threatening to do this for a while now. It must be over 6 years if I believe what Lisa told me. And where'd she disappear to?
Right in front of you.
Oh, I'm there. Aging sucks.
One of these?
Yeah, well, I've got several of them, but you gotta switch around. There's haves and have-nots. Some have spent our whole life being sunburned by oscilloscopes, and we kind of take them for granted. They're really powerful instruments. And then there's other people who didn't have that advantage. And part of the problem in the radio world is that we're dealing with, 50s, 40s, 30s radios. And in those days, there were oscilloscopes, but they were expensive lab instruments. The people working on radios didn't have them. So like you read the textbooks, they don't know nothing about scopes. So we're going to try to take care of that this morning with the Scope School, or as Walt Hesketh dubbed it, Scopes for Dopes. So the schedule, and we're on schedule here. The students have arrived, and we did meet and greet. I have an introductory presentation here for about 15-20 minutes, and then we'll move on to the main presentation. After that, we'll break out into the learning activity stations, which are set up all over the place here. And this is going to be self-directed. What you need to do is float around, spend 10 or 15 minutes at each place and try, see what's going on and see what you can learn. There'll be pizza in the middle of this somewhere. We'll try to wrap up about 3:45 and get out of here at 4 o'clock. Well, the word oscilloscope, and sometimes that tells you a lot. From the Latin oscillare, to swing, plus old modern Latin scopium from the Greek, to examine. So this allows you to examine oscillations. Now, there's another instrument called an oscillograph. That's why that name got used up first. We'll talk about that briefly. I threw the Maxwell slide in here because for us, this is really where this starts. And this guy was you had Isaac Newton in the 18th century. This guy was the preeminent theoretical physicist in the 19th century. And what he did was he took the existing equations for electrical and magnetic fields and wrote his own equations, which graphically show you that if you have an alternating current traveling in a conductor, that it's going to generate electrical and magnetic fields around it. And oh yes, they're going to move away from the conductor at the speed of light and take energy with them and not come back. What? Well, eventually, that forms the basis of radio, and other scientists followed on to that. Sort of an interesting story. But the message here is that you end up with these high-frequency oscillations that are, at least 1 million times per second. So normal ways of observing these things just don't cut it. In fact, even just getting those kind of high-frequency currents was tough at the beginning, and what they ended up doing was, here's a high-voltage transformer and some Leyden jars, capacitors, and an inductor and a spark gap. And what happens is, on the swing of the voltage, the low-frequency AC here, on the swing of the voltage, the caps charge up till finally they can arc over the spark gap. The energy in the cap goes through the gap into the coil, causes a magnetic field there. Then the arc goes out, magnetic field collapses, everything comes back around the other way. And this happens at electronic speeds, generating high-frequency oscillations. Or so the theory said. Here you are in 1860, 1870. How do we even know? You see the spark, but how do we even know this is doing anything? So we need ways to observe oscillations. Here's an early one. This was in Ambrose Fleming's book in 1913, but a picture was from much earlier. And what they did, set up one of the old cameras, looking at the spark gap, and in the back of the camera they had a photographic plate that was being turned by a motor. And so they let the spark do its thing, and sure enough, you can see the spark goes on and off, and if you know the rotational speed of the film, you now know the frequency of the oscillation. So that's the kind of way, the kind of things that were necessary to observe oscillations. Of course, this is kind of a pain in the neck. You've got to run to the darkroom with the film and all this kind of stuff, but it was a beginning. That led to mechanical instruments that did such things. Here's an oscillograph. And this thing involves sort of a meter movement and a moving mirror, and again, film in the back here. And after you come back from the darkroom, yes, indeed, you can observe high-frequency oscillations, although you're kind of limited because you're talking about a moving mirror that just can't vibrate very quickly. So that doesn't solve the radio problem either, but that's a stake in the ground, and that's where the word oscillograph got used up. So we get to 1870, a guy in England named William Crookes, and he's messing around with tubes with some of the air pumped out of them and spark coils like this guy in the back here. And he builds this thing, and when he turns the spark coil on, the front of the tube glows green, and oh yeah, he's got this metal Maltese cross in here, and it leaves its shadow on the front of the tube, but in fact these are on a hinge. You can flip them down and the whole front of the tube glows green. So very, very curious. Here's another picture of the same thing. And what happens here, high voltage is applied here, and you can see the gas flowing from the discharge. And they found that the negative end of this thing, positive here, negative here, was causing something to spray out in this direction. They called it radiant matter, and later called it cathode rays, cathode being the negative terminal. And now we know that what happens here is that you get this discharge going, positive ions come off this electrode, bombard this thing, get it hot enough that it emits electrons, and they're drawn back out by the positive field, but they're ballistic, they're going in a straight line, so they go right out, hit the front of the screen. I don't know if there was some special additive to the glass to make it glow or not. So based on the Crookes tube, we get Carl Ferdinand Braun, as in all the Braun appliances from Germany. And he develops a cathode ray tube. You have the cathode down here, a high voltage terminal here. I guess he had another terminal out here. He has the innovation, he has a mica screen in here with real phosphorescent material on it. And there's a plate here with a hole in it that constricts this to a beam. And sure enough, he can get a spot on the screen. And he also finds out that if he puts a magnet near the screen, he can move the spot back and forth. Of course, you got to remember, we still don't know what's going on inside this tube. You know, it's radiant matter, or whatever that is. He had an associate working with him, Johann Adolf Wilhelm Zenneck. Zenneck, he puts two magnet structures out here, and now he can get XY deflection. And he can use one signal to sweep the beam. This is forming the x-axis in a graph, and now he can observe the other signal moving the beam in the y-axis on the screen. So that was Braun, really the original oscilloscope, 1897. At the same time, We had another Brit, J.J. Thompson, and he's working in the same area. His cathode ray tube, this thing here that looks like Flesh Gordon's spaceship. Rather than magnetic deflection, he has metal plates inside the tube, and he observes that this radiant matter coming out the back here can be repelled by the negative plate, so they must be negative widgets of some sort. He does further work. He identifies these as particles that are 1,000th the size of hydrogen atoms. Does a lot of other work. He discovers the electron in effect and is credited with that. So now we know what's going on inside the tube. Now we know there are electrons. Braun showed us how to do magnetic deflection. Thomson showed us how to do electrostatic deflection, and we're on the move. So I'm going to go real quick now. Oscilloscopes get developed. They find out about thermionic emission and heated cathodes and things like that, so you don't need 50,000 volts on the tube, which is a bad deal, by the way, because then you get hard X-rays coming through the glass. But never mind. Alan Dumont, local boy makes good. I thought this was kind of cool. He was born in Brooklyn in 1901. Grew up in Montclair. His father got him a building a crystal set in 1913, and it was downhill from there. But Dumont built probably the best oscilloscopes up through the World War II era. Was influential in electronic television and the development of CRTs. Local kid. That brings us to these guys. Howard Vollum and Jack Murdoch. Vollum actually worked here at the Evans Signal Laboratory during World War II doing CRT things. Radar and whatnot. And probably played with Alan Dumont's oscilloscopes. And after the war, he goes off and now he knows what an oscilloscope really needs to be. He founds Tektronix. He invents triggered sweep oscilloscopes, and you'll hear about that in a little bit here. And so this is one of their original products, the 511. And you know, you look at these things, and you're used to a radio where there's a volume control and a tuning knob. Well, now all of a sudden, you have this whole ocean of controls, and you say, "Oh my God, what are we going to do?" And so you kind of feel like this.
Now that I can understand.
Okay, that I can understand. In fact, I wanted to ask you about what do they call it? Unusual attitude training.
Mm-hmm.
You're going to fly an airplane. You've got this hood in front of your face, so you can't see what's going on. And the instructor puts the airplane in an inverted spin and lets go of the controls, and now you've got to sort it out. Okay, now this is the problem you're facing with oscilloscopes. Of course, you have the advantage that the ground isn't going to reach up and smite things, which is what happens in an airplane. So don't panic, relax and enjoy this, and learn to fly these things. I mean, the people that use them, they're oscilloscope pilots. That's the way you feel when you sit down and do a strange scope, and you got to sort it out a section at a time and get it going. You'll sit down in the scope, there won't even be a trace. You know, and step one, you got to learn how to sort through these things, and that's one of the things I want you to do today. Whenever you come up to a scope, kind of sort your way through it. In fact, people running the displays mess up the scope before they get to it. You know, so you want to learn to be a little bit comfortable with them and how to make various measurements and things. Okay, to that end, I have professional assistants this morning. We have Alan Wolke. Alan's a field application engineer. Yes, Alan is a field application engineer working for Vollum's company, Tektronix. So if there's something to be known about scopes and he doesn't know it, you're out of luck. So, take it away.
Al said, I worked for Tektronix, but I've really only worked for Tektronix for the last 4.5 years or so. So I spent the first 25 years of my career as a design engineer, oscilloscope pilot. I tend to call myself that, because indeed, when you drive these things, you do kind of feel like a pilot. It's kind of flying around what's going on inside the circuits. So I actually worked on this facility in 1983 and 84, a couple of buildings over for the net radio division at CENTCOMs back then. So, but that was in between college semesters, and they offered me a job when I got out of school, but I found a better job in the private sector, unfortunately. So, but here we are back again. And I think this is so cool because I don't think there's been this many oscilloscopes fired up on this facility in 15 years. This is just really cool. So I spent 25 years as a design engineer, application engineer, primarily working on analog circuits, high-speed circuits, and things like that at the transistor level. So you guys know a lot more about hollow-state vacuum tubes than I do. So the little circuit I've got up here that we're going to play with a little later is solid state, so you have to forgive me for that. So so I'll do that part. So a couple interesting tie-ins, I think, from Al's excellent introduction. This oscilloscope right here is an Alan B. Dumont oscilloscope. And you can't really see it, but what it says up there is cathode ray oscillograph. So it really kind of borrowed the oscillograph term from the old, the photographic type oscillograph, and then the discovery of the kind of cathode ray capability. So Dumont called his scopes cathode ray oscillographs, which is pretty cool. So this is an old model 304. I used to have one of those. And we'll talk a little bit about what's different between a scope like that we would call a recurrent sweep scope. You'll understand what I mean by that in a little while. Versus like a triggered sweep scope. This is a Tektronix 465, and there's a couple of them here. There's one here, and there's one on almost every table, it seems. But it really was probably one of the most popular analog scopes that Tech made. But the idea here is I'm going to show a lot of different scopes and things like that, and talk about each of them in the sense of where all the controls are, where to find things. We're going to talk a lot more about what all the controls do. Break them down into groups and things like that, so it makes it easy for you to try to understand all the systems. So it's like, okay, if I have a signal, if I adjust this, what am I adjusting? What am I looking at? What do I adjust to get this, and how do I get a trace on my screen, and how can I interpret that? And again, I want this to be interactive too, so if there's questions that you have, if something isn't clear, stop me, that's why I'm here. And this isn't a can thing. I'm not trying to sell you anything. I want to help you guys get the most out of the equipment that you have. Okay. Now, actually, the first oscilloscope I had was actually the Model 304 from Dumont. I actually bought it from the high school electronics laboratory where I went to high school in Madeline. Because they didn't know what to do with it. Oh, I know what to do with that. I hooked it up to my stereo so I could see. But I learned an awful lot about just what it could do just by playing with it. And that's what you learn with these things too. The more you play, the more you learn about it. So an oscilloscope is really made of a couple of different systems. There's a display we'll talk about first, where you're actually seeing what's going on. We'll talk about what it is and how you use it and that kind of a thing. And then various sections to drive what you see on the display, both vertically and horizontally. Okay. So we're going to go through, kind of each of these sections. And no matter what kind of scope we have, whether it's some of the older recurrent sweep scopes or some of the more modern scopes, and even to a large extent, even the digital scopes, a couple on the table up here, there's one or two else around on the tables, still have largely all these same sections. They get more complex as you go in, but they all have that same basic block diagram. So the fundamentals are all kind of the same. So let's talk about the display first. Notwithstanding the digital scopes, which have a digital computer type display, all the scopes that we typically use have a CRT or cathode ray tube. And all the scopes that I have except for one, and I own more scopes than any human should. I brought 5 with me, I have like 4 or 5 more at home. So don't ask me why, but I think the same passion that you guys have for fixing up old radios I have for fixing up old scopes, I think, that's what it comes down to.
So in my place, you lay back, I got about 6.
All right, there you go. So let's start. So the display tube that we kind of talked about basically is one where an electron beam gets accelerated towards the face of the screen, and the face is kind of coded so that when the electron beam hits it, it glows. Okay, and has a little bit of persistence. So even after the electron beam leaves, it glows and it decays out. Okay, and the way that everything works here is that we're going to drive that beam and move it across the screen up and down and left and right. Okay. And as it moves, it leaves this trail. okay, that you can see, visually see. On the screen itself, you'll see a couple, things like divisions and things like that built up on the screen. This helps you to make measurements. By looking at how far the beam gets moved, you can actually make measurements of voltage and timing and frequency and things like that. Most of the scopes will have 10 divisions horizontally across, which makes it kind of convenient to, kind of count out frequency and things like that. And we'll have little minor divisions in there so you can make some determinations if you want to make some calculated measurements or calibrated measurements. They'll either have 8 or 10 vertical divisions. Okay. And we'll talk about why the divisions are important and how you can use that when you're making some measurements. Okay. But at the end of the day, basically all these tubes work the same way. We've got an electron beam that gets shot out of the electron gun. Most of the scopes, probably almost all of them here, use what's called electrostatic deflection that Al mentioned, where basically the voltage potential between these two plates, both vertically and horizontally, will determine the position of the beam at any instant in time. And if you start changing these voltages versus time, you can move that beam versus time. That's really the whole idea of what an oscilloscope is right? Allow us to see how voltages are changing versus time. Okay? So if you could basically take your Simpson 260 and stick it in your radio, and if you can watch that the meter movement could trace the voltage fast enough, you'd actually be able to see what's going on. Well, that's what the oscilloscope does for you. Rather than trying to have a meter movement and follow it around versus time to see how the voltage is varying, the oscilloscope will essentially move the beam around in response to how the voltage is changing versus time. So it allows you to visualize what's going on with these alternating voltages. Okay.
That's a great analogy.
So that's clearly really what it is. Now, it's not a substitute for a multimeter, right? In some cases it can be, but in many cases it gives you a lot more insight. And you might find yourself using it a lot, where you could use a voltmeter, but you might get some more insight by using the scope once you get comfortable with how to use it. And the more you use it again, the more comfortable you get with it, and the more you'll learn out of it. So let's start off with the display system. Okay. Remember, we've got a vertical section, a horizontal section, and we've got our display system. It's kind of another way of, I like showing different implementations or different drawings of the same concept because one of these might resonate with you. Okay, see what's going on. So in the CRT, remember we're going to be driving, a beam horizontally. That's kind of called the x-axis, or the horizontal time base. We're going to drive vertically, which is really going to most of the time in response to a voltage that you're probing or looking at. Okay, and they're driven by. I'm just going to back up here. You're right about this thing. But so we kind of draw these deflection plates because the horizontal deflection plates are going to move the beam horizontally. Okay, and the way to kind of picture that is that we're really just tracing this beam across the screen at ideally a known rate. So many microseconds per division or milliseconds per division. How quickly we're going to move the beam from one edge to the other. And as we're moving that, the voltage we're applying at the input we want to measure is going to bounce that beam up and down. Okay, but we're just moving this. We can move it quickly, or we can move it very slowly. Okay, and that's done by just applying the appropriate horizontal voltage difference between the horizontal plates. So you can almost envision that the voltage that's driving on those plates is a linearly changing voltage, like a ramp, right? So at one end, the beam is all the way at the right, and as that voltage rises, we start moving the beam across to the other side. And then once we get to the other side, what happens? We very quickly reset it back to this side and do it again. So you get the sawtooth kind of wave that's used to drive the beam horizontally. Okay, and when we make it, we'll talk about how we make adjustments to that to look at different sweep speeds and things like that. But the horizontal section of the scope is really used to drive that horizontally across the screen. So there's really no input from you other than telling you how fast you want it to go. The vertical side, okay, is driven more by whatever signal you're looking at. That's going to drive the vertical deflection voltage, and therefore tell you where the beam is as it's sweeping across. Pretty simple. The display system itself has some controls, okay, that are separate from the other controls. Typically, you'll see things like this. You'll see focus and intensity. They're kind of self-explanatory. Okay, change the focus of the beam that's going across the screen, the intensity, how bright it is. There's also a trace rotation. On most of the scopes, you'll see it. It's usually a little set screw as opposed to a knob. And that's because depending on where the scope is and what the magnetic field is, where you have it sit, the trace might be tilted one way or tilted the other way. You just go in there with the tweaker and kind of adjust it up and get it kind of sitting flat. Okay, so it doesn't mean there's anything wrong with the scope. It doesn't mean that you have to go in there and twist the tube around to kind of get it right. Some scopes do have that because they don't have a trace rotation control. But if you see a trace rotation control, that's what it is. Okay. There's also this this one here called beam finder. Now, not all the scopes have this, but another thing that Al mentioned, the unusual attitude control. How do I not crash into the ground? So you walk up to a scope, you turn it on, and you don't have a trace. What do? It's like, oh, okay, now I got to get myself out of there. Well, some of the scopes have a little key here called a beam finder, which helps you. And what it does is it reduces the vertical and horizontal deflection voltages enough so that the beam, if it had been adjusted way off the screen, will now be shown on the screen somewhere else, and we can go find it. Okay, let me show you an example on a scope here. In fact, you should be able to see it looking on the screen here. I'll just kind of play with it on this one. So let's say, for example, somebody had taken this thing vertically and adjusted it way off the screen. It's like, oh, where'd my trace go? If I hit the beam finder button on this guy, which is right here, oh, I can see that thing sitting up there. So I know I have a trace, but it's somewhere off the screen. Okay, so if I go in here and I can actually adjust this down, you can actually see that trace move. Oh, look at that. Now I know it was there. Okay, if it was adjusted horizontally, okay, and vertically somewhere else, I can say, okay, I know I have a trace, it's somewhere over there. You can go play with it, or you can leave this button pushed in and kind of go say, okay, I can get it centered on the screen here. I'll bring it back up in. So it helps to identify or find a trace that might be thrown off the screen somewhere. Okay. Again, not all scopes have it, but it is a kind of a convenient little feature to have, if your scope's equipped. So those are some of the controls that you'll have that are just dedicated to this display system. Okay. And what you'll find, most oscilloscopes are trying to arrange all these controls in a logical way. I would imagine, the cockpit of an airplane for people who don't fly like me, it looks like a sea of buttons and knobs. But I'm sure there's some logical arrangement for how things are arranged in terms of, this is for this, and that, all the different functions for flying a plane. The same thing is true for any of the displays or any of the controls on a scope. You'll typically find some of these CRT or display system controls arranged kind of in about the same area. Usually, not always, but usually. It's the manufacturer that's friendly to you. So the next kind of section that we're going to talk about, because it's the one you'll use a lot, is the vertical system. Remember, the oscilloscope, we're hooking up to a circuit inside of a radio, whatever it might be, to observe what's going on with those voltages over time. Okay. So the vertical system is what's going to drive, we're going to basically be applying our signal to the vertical system of the scope. And that vertical system, its controls are going to control where and how much we're going to deflect that beam vertically in response to the circuit, to the node or the voltage that you're looking at. Okay. So there's a lot of different controls. There's a vertical attenuator. The reason we'll describe this a little bit is kind of taking the analogy of a super heterodyne receiver. Okay, why do people do superhets now instead of a tuned front end? One reason is a tuned front end is really tough to get a tuned front end that'll tune over a wide frequency range and still have the same skirt shape and things like that, good selectivity and things like that. It's a lot easier to use a super heterodyne type of architecture where you take the frequency of interest and drop it into an IF. Now all your filtering and gain is all done at a fixed frequency at the IF. You're just putting what you want into that IF. So it makes the design easier and makes the overall function of that radio a lot better. Same thing happens on oscilloscopes. Okay. For the oscilloscope vertical system, we've got to develop an amplifier that can take the input signal that we're putting in and generate a big enough voltage to drive the deflection plates of the scope. Now, if we adjusted the gain of that amplifier all over the place, its response may not be so linear. So the way oscilloscopes are typically designed is that the vertical amplifier section is typically a fixed gain type thing. And what we do is just throw an attenuator, a passive attenuator on the front that you can adjust. Okay? And that adjusts the amount of voltage input to this fixed gain amplifier. So that's the way you get different voltage scales for the front end of the scope. Okay? So you just have a fixed gain amplifier. Okay. Some of the controls that you'll see on the vertical system, you'll see a coupling control. And this controls how the signal that you're putting into it gets coupled to that vertical amplifier. And that's typically either AC or DC coupling. Okay, we'll talk about why we might want to use those. You'll also typically see either a volts per division control, which tells us how sensitive we're going to be. So it tells us if I apply a 1 volt peak-to-peak signal, and I have the scope set to 1 volt per division, I would see 1 division of reflection. on there. In fact, if we look at this scope here, you see this little 2 volts right here? That tells me this is set to 2 volts per division. And this signal, which is occupying, about 2 volts, it tells me that it's a 4 volt peak-to-peak signal. Okay. For AC or DC coupling, why would we want to do that? So DC coupling, as you would imagine, whatever we've got coming into this input is going to be applied to the vertical deflection. So if you're looking at, say, the output of say the plate of a circuit, the plate might be sitting at 300 volts, but you've got a 2 volt signal sitting on it. Okay, you'd have to adjust the volts per division to something like 10 or 20 or 30 volts, 40 volts per division, in order that the DC voltage doesn't drive you way off the screen, but then the AC riding on top of that is really small. Okay, another good application is looking at ripple on a power supply. Okay, you want to look at how much ripple we have on a power supply. Okay, you can, if you DC couple, you'd have to get a very insensitive setting, like 50 volts a division, 100 volts a division, and then you might not be able to see the ripple. So if you go to AC coupling, that removes the DC component and allows you to use a much more sensitive setting to measure just the AC variation that's riding on top of that DC bias, wherever it is. Okay? So you'll see a coupling control, you'll see volts per division. Those are kind of typical controls that you'll have on the vertical section of your scope. Okay? You'll also have a position control. That's kind of obvious. You adjust that, it moves the trace up or down. Okay? Most of the time you've got the trace centered, but there might be cases where you want to move it somewhere else, because you might want to say, well, I want to look at how all my voltages are changing with respect to some power supply voltage, or maybe to ground. If I know everything is, say, at ground or above, I might say, move the position so that when I touch ground, it's sitting down at the bottom, so I can actually look at the voltages and where they are with respect to ground. Okay? So the position helps you go do that. Okay? And in the mode position, we'll talk about that a little bit, because this, you really get into that when you have multiple inputs, multiple vertical channel inputs. And there's really some good reasons to use, like a 2-channel input, as opposed to just looking at 1 channel. There's some insight you can get by looking at 2 channels at once, 2 different parts of the circuit at the same time. Okay. So we'll talk a little bit about those too. What you'll see, and I brought these up just to show a couple of examples of what the vertical scale and coupling controls look like on different scopes, so you kind of recognize them. And again, they'll typically be kind of grouped together, usually around with where the input connector is. Either it's a BNC, or some of the older low-speed scopes might be a set of banana plugs or something like that. But you'll see you'll see the input. Here's a coupling control, AC or DC for this one here. Okay, here's my volts per division control right here, and the position. Okay, so that's on that particular scope. Here's another one that has AC or DC coupling right here. Here's the input. There's my vertical position, my volts per division here. Here's another one here. This particular scope has got both the ability of changing the input impedance here from what most scopes are, which is 1 megahertz. You get up to higher speed scopes, and you have usually an option to go to 50 ohms, and the really high speed scopes are only 50 ohms input. Okay, this particular one could be either. Okay, and here's an example of this AC or DC coupling. Okay, let's say I had this little wiggling signal sitting, several volts above ground. If I was DC coupling, I could look at it like this. Okay, but by AC coupling, I can get rid of the DC component of that and just magnify up and look at just the AC voltage. Yeah.
Now, why did you want to reduce your input impedance from like a high level down to like 50 ohms again? I missed that.
That's a good question, and it really gets to when you get to high-speed circuits, okay, or RF circuits and things like that. RF circuits will be affected more by things like straight capacitance and things like that. So even if you've got a circuit or you've got a 1 megohm input impedance, that 1 megohm input impedance might be internally shunted by, in this case, 15 picofarads, in that case, 20 picofarads. That's going to dominate the impedance at those high frequencies. Also at high frequencies, you've got to be concerned about doing impedance matching, okay, of the connecting line, like a piece of coax, which is usually 50 ohm coax, and impedance match that at the end so you don't get reflections and problems like that. When you're dealing with sub couple of megahertz type signals, you generally don't have to worry about it too much. Once you get a couple of megahertz and above, you have to start sometimes worrying about impedances and reflections and things like that. And typically once you get up into those regions, a couple of tens of megahertz or more, you're generally working in a controlled impedance environment. Okay, and where a 50 ohm termination is the way to go. Typically, like anybody who's a ham, it's like tune a transmitter into an into an antenna. You're doing an impedance match to get the most power transfer, minimize reflections and things like that. Answer your question? Okay. So one thing to take note of, maybe when you look at the other scopes around, is almost all of them should tell you what the input impedance is. And probably almost universally you'll find that the input impedance is 1 megohm resistive, but then probably has got some amount, anywhere from 10 to 30 picofarads of capacitance or so. And that'll become important in a little bit when we start talking about how you connect up to your circuit and probes, okay, and the impact of what that input impedance is and what it might do to your circuit. And how many of you guys have been ever working on a radio or something like that, and just the simple act of connecting your test equipment changes the way it works? Sure. That doesn't happen, right? Well, that's because what the load that you're presenting with that probe or your test leads or whatever is altering the way that circuit behaves because it's sensitive to that load. So that's one of the reasons we use probes, is to minimize that kind of loading, to minimize those effects. We really want to look at the circuit without making the circuit do anything different, right? We just want to see what it's doing. We don't want to change it when we touch it. It's like a doctor, it hurts when I do this. Well, don't do that, you know? So we want to make sure that we don't have those kinds of problems. And so you have to start worrying sometimes about what the input impedance is, and we'll talk about circumstances where that's really important. Everybody clear on that? I said, so when you go around, you'll find on the various scopes that are around, these sets of controls will kind of be grouped together. We look at the scope here. Okay. So this one here that we were focused on, I got some of the display controls down there. Okay. We've got intensity and focus, and so if I adjust the intensity right here, I can kind of make that bright or dim. Okay. I've got my focus control over here. Here's the focus. I can make it kind of fuzzy. Okay, or not. So they're all kind of grouped here. The vertical controls for channel 1, channel 2 are sitting right here. There's my position controls right there. Okay. And again, they're all kind of grouped together, kind of logically. Okay. So another thing that we'll see are the mode controls. And again, this is really when you start dealing with multiple channels. How are we going to display multiple channels? Okay. We're looking at 2 inputs at one time. Well, most of these oscilloscopes, except some of the older ones that Tech used to make called dual beam oscilloscopes, have really just one electron beam. So how am I going to have 2 channels displayed with just one beam going across? Okay. So it all depends on how we set up the vertical mode. Okay. So obviously we can say select channel 1 or channel 2. Okay. By selecting channel 1 or channel 2. Okay. So that just picks 1 or 2. We're only looking at one signal at a time. Now if we want to do both, there's a couple of ways we can do that. One is something called alt. Okay. Alt means we're going to alternate between one channel or the other, which means that one sweep goes across and shows you what's going on channel 1. Then the next sweep that comes across shows you what's going on channel 2. The next sweep comes across, goes back to channel 1, and we alternate back and forth between. Okay. That's what the alt means. Now alt works well if the sweep speed is going fast enough that you don't see this thing bouncing back and forth between the 2 channels. Okay. If you're looking at really low speed signals, it can be kind of annoying because you're going to see one channel and then the other one and then the other one and the other one sweep through. When the sweep speed is going fast enough that you don't see the sweep, it just looks like a solid line, then the alt is fast enough that it's a good way to go. So in those circumstances where the alt would be too slow and annoying, there's another mode called chop. Okay, so it's called here. See, here's my chop and alt. Is turning that button here. I've got alt and chop here, and I've got alt and chop right here. You'll see them on some of these multi-channel scopes. So what the chop does is that very quickly bounces back and forth between the 2. Okay, so you don't really perceive it. You don't see it. It's going fast enough that you don't see it. To you, it just looks like 2 solid lines going across. Okay, as an example, let's do that on this scope here. I'm going to turn on channel 2. So you can see I've got 2 channels on this scope right now. And right now I'm actually in the alt mode. So if I slow this way down, see, I've got these 2 traces alternating back and forth. Okay, so if I had to be looking at that slow of a sweep speed to this, that wouldn't be very convenient. But if I go to the chop mode, it looks like there's 2 continuous lines going across because it's literally chopping back and forth between the 2 very quickly, not in between each sweep. Okay, and we can speed this up and go look at this. And what we'll find is in the chop mode, you see how sometimes the tracer, you get this little diddly pattern in there, because now we're starting to kind of resonate almost with the chop frequency, and now at these speeds maybe the alt works a little bit better. Okay, so it really depends on which sweep speed you're working with will determine whether the chop or the alt is the right one. In some cases, either one will work fine. But it's those extreme cases where one will always work better than the other. Okay, but that's what the chop and alt does. Okay. Now, yeah.
Is there, you had mentioned that some of the older scopes were actual dual beam.
Yes.
When I was in the Navy, we had a whole bunch of beams in one tube. I think it was
Yep.
6 beams in
Sure.
one tube for electro countermeasures where you can see a whole bunch of different things.
Sure, sure.
Anyway, the question I'm asking here is, are all the scopes now single beam or are they dual beam?
Well, it's a good question. The reality is that there are not a lot of people making CRT-based oscilloscopes anymore. So most of the scopes that are being made these days are digitizing scopes, where the signal comes in, gets digitized by an analog to digital converter, and then those samples get displayed on a computer-like display. So in effect, we're sampling all these signals at the same time. So if it's a 4-channel scope, it's 4 channels, and then the display is just showing you the result of those. There isn't really a sweep or a beam associated with each one anymore. Okay. I would say that the vast majority of what you'll see out onto the market, and like the scopes that are here, are single beam oscilloscopes.
There's a good reason for that, the weight.
That's true. That's one good reason. I know that some of those big dual beam scopes at Tektronix were room heaters, they were heavy. They're great scopes, but they're big, expensive, absolutely. Okay. So another
Yeah,
note that
tell them how many tubes are in one of those.
a lot.
Yeah.
There was an awful lot of tubes. Some of them were made specifically by Tektronix in Beaverton, Oregon, for the scopes. That weren't other tubes you can just get out of the TV repair shop. It's interesting. Some of them literally had 50 or 60 tubes. Walt here built a scope with 2 pentodes. It's awesome. Down under the table, I'm sure we'll be happy to show it to you. They did a great job on that. So another mode is where we can literally add the 2 signals together. That's kind of interesting. That there might be applications where you want to add the signals, and it's like, well, maybe, maybe not. But what's really interesting is sometimes using the add mode in conjunction with being able to invert one of the channels. So if I can invert, say, channel 2, and then I add it to channel 1, the resulting trace is now the difference between channel 1 and channel 2. So this allows you to look at the voltage across a component or a device or a chunk in your circuit. Okay, to literally see what that is doing. Okay, if it's an amplifier, it's supposed to amplify by a factor of 2 or something like that. If you subtract the 2, you can literally look at the difference to see if there is a voltage difference between the 2, if there's a phase difference between the 2. So by adding and inverting one channel, you can see in this case I can do an add, and I can do a channel 2 invert. So if I flip both those switches there, or if I do an invert of channel 2 and an add, then I get the voltage difference. It's like a differential voltage measurement. So it's like taking your voltmeter and going across a component. Okay? A scope, all the measurements generally are ground referenced, right? One side of the probe is connected to ground, and the other side goes to the voltage you're measuring. You can't take that ground and connect it somewhere else to go across the component, because now you're going to ground that thing. Could be bad. You let the smoke out of something once. So by being able to look at, with 2 probes, one connected to ground on one side, and then the nodes you want to look at, by inverting one and adding them, you essentially can look at the voltage difference across that particular component or device. Yeah?
A really simple question. A dual trace could be a single beam?
Yes?
That's 2 different.
Yeah, so these 2 scopes here, this one is a 2-channel input, that one's a 4-channel input. Both of them are single beam oscilloscopes, but you essentially can get 2 traces like I have right here, right? But it's because it's either alternating back and forth or chopping between them. Okay. Good? Okay. So this is just some examples of what you'll see kind of a vertical mode, and it really is more important on multi-channel input scopes as opposed to a single-channel scope, because you don't have all these other things to do that with. So those controls are missing from the single-channel scope. You'll typically find them on multi-channel scopes.
Is there any advantage in, what do you give up when you use a single channel scope? I mean, you give something up as opposed to a dual beam scope?
Well, I would say, let's make the distinction between single or multi-channel versus single or dual beam. Okay. I would say let's not even talk about dual beam because it's likely you'll never come across them. So let's just talk about single or multi-channel. I think that makes the most sense for what you're going to come across and use. And even from a dual beam scope, you're still going to use it like a multi-channel scope. It works the same way. So the advantage of having a multi-channel scope is that it does allow you to see what's going on in your circuit in two different places at the same time. And I'm going to show you an example of where that could really be useful to give you some insight to see what's happening. It might be useful sometimes just to go along and trace a signal through your radio and say, okay, it should be doing this here, it should be doing this here, boom, 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 and it works. But if let's say you're checking out like an audio amplifier, okay, you know the input's going to be a small signal, the output's going to be a big signal, and you can just bounce back and forth between the input and the output and look at the relative magnitudes of two. But if you have two channels, you can look at the input and the output at the same time and just compare them, okay, without having to move back and forth.
I mean, there is no advantage in using a dual beam scope.
For what you guys are doing, no. I think that'd be a fair statement.
Lower sweep speeds, you have continuous sweeps, so it doesn't bounce at all.
Yeah, but as it really
I think what it is in the old days,
Yeah.
they couldn't do this alt and chop and all the switching
right.
cleanly enough to
Yeah.
make them work. So you put two electron guns in the tube and you have two separate beams and you don't mess with that stuff. Like he says, low speed waveforms.
Yeah, and you could vary the intensity of each beam independently. You can't do that with a single beam scope.
Okay. In an ICU, when they're monitoring hearts and things like that,
Yeah.
that's slow sweep.
Right. Right.
And I just was, at one time, of course, today they're solid state.
Yes.
But at one time,
They were
were actually multi-beam.
Yeah. So you could adjust each one, the focus, the intensity, and things like that of each one independently.
Okay, I understand why you would want to use that.
Okay. So let's kind of move on to the horizontal system. Okay, so now we kind of know what the controls are to couple our signal in, how to adjust it, AC or DC, how to combine channels if we want. We'll go play with some of that. Actually, let's go do that a little bit here. Well, I've got this hooked up to a circuit. Actually, let me quickly draw what that circuit is. And again, you've got to pardon me because I'm from the solid state world. So the little circuit I put together is a transistor circuit. It's not a, so you have to forgive me for that. So hey, I can leave now. So I got
We'll make an exception.
Okay, we'll make an exception here. Okay, so I got a positive supply here. I've got I basically did a little transistor amplifier that looks like this. Okay. So simple little amplifier. This is my input. This is essentially my output. I could also look at the signal here as well. Okay, so that's all I've got. I've got connected up a signal generator to here. Okay. And the way I've got this set up right now is I have one probe, channel 2, looking here. And I have channel 1 looking here. Okay, that's what I've got set up on the bench over here. Okay. And so what's interesting is if we take a look at this, I can adjust, say, the amplitude of the signal going in. All right, and I can see the amplitude of both of these guys changing. Now, for those of you who are familiar with transistor circuits, this is more like an emitter-follower, right? So the voltage swing that appears here is going to be about the same as the swing that I see here. It's just going to be dropped by about 0.7 of a volt. Okay, so essentially I've got unity gain from that point forward. And I'm going to have some gain associated here, dominated by these two resistors. Okay, so the resistor ratio here is going to kind of determine the gain, and it's an inverting gain, right? As this voltage goes up, okay, this voltage goes up, which means this current gets larger. So if that current gets larger, this current gets larger, so the voltage drop here gets deeper, right? So it's an inverting amplifier. So we can actually see that because I'm looking both here and here, and if we look at this, I can see that when this guy is going up, this guy's coming down, right? Because I'm looking at the same time. And I can also see it's got a gain of about 2, or I should say, more accurately, -2. Okay. Now, where it becomes interesting looking at two channels, let's say I was only looking at one channel. Let me turn one of them off. And let's say I adjusted the DC offset voltage of the signal I'm applying here. If I raised it or lowered it, what can happen? If I lower it too much, I'll get to the point where I turn the transistor off, right? Because this voltage goes down and it won't be high enough to turn on that junction. Or if I raise it up too much, I can reach a point where I saturate the transistor. Okay? If we adjust the DC offset here, okay, you can see I can adjust that's the output moving up or down. If I go up too far, ooh, I start to clip, right? Okay, so that's really where I started to turn off the transistor. Okay, if I go the other way, there's some wacky looking stuff going on there. Okay, see how the waveform kind of distorts. Now you get a lot more insight if we turn the other channel on here. Okay, and now I can see if I adjust that same DC offset, you see when I bring this down, you see how the bottom of the input waveform is kind of getting cropped at the bottom and turning the transistor off, and it's also corresponding with that. If I take my coupling here, if I change it to ground, I can see ground is sitting right down there at one division up from the bottom. Okay, so let's go bring that back up. Okay, and now, so if I bring that signal too far down, let's cut the transistor off, and I can see what it looks like on both sides. If I bring it up too far, I'm going to start bringing the collector and emitter voltages close to each other, which means I'm going to start to saturate that transistor. And you'll see they'll crash right into each other here. Boom. Okay, that's saturating the transistor. Where if I'm looking at that just on the one channel, it's like, oh, that's a weird looking waveform. Why is it doing that? It helps sometimes to look at both of those signals and say, oh yeah, I'm crashing these voltages. The voltage here is collapsing down to nothing and saturating the transistor. So you get some insight sometimes by being able to look at multiple channels at the same time. Because you say, like, well, the signal looked normal here, it looks bad here. How do they look with respect to each other? It can really be helpful sometimes to look at that. Okay. So by playing around with the vertical controls and things like that, we can look at multiple channels at the same time and get some insight to what's happening. So I want to kind of do that before we get into the horizontal section, because we're kind of leaving the vertical section alone here for a moment. Let's talk about the horizontal section. The horizontal section is what controls how fast we're pushing that beam across the screen. It's like, you know, how fast am I, if I took a pen and I was writing out my voltage levels versus time, how quickly am I running across the screen there with it? Okay. So the controls there primarily control, let's back up here, primarily control, you'll see something called seconds per division, or some measure of time per division. How quickly does it take the beam to move across each division of the scope screen? Okay. Now, on some scopes, you'll see, instead of seeing a seconds per division, you'll see a frequency range. We'll talk about the difference there and why some scopes have that. As an example, over on the table over here and a couple of others. We'll talk about the difference between those two. You'll also see a trigger control. You'll also see a mode control there as well. It's like we had a mode control vertically. We've got some mode controls for the horizontal as well. You'll also see a position control. Okay. So let's talk a little bit about what's going on with these. Okay. So we're in general, anytime we're moving the beam across the screen, we call that a sweep. Okay. So how fast are we sweeping that beam across the screen? And how do we do that? The earlier scopes, like the Dumonts, okay, and some of the other scopes you have around here, some of what we call the service type scopes, use what's called a recurrent sweep technology. Meaning that that horizontal, that sawtooth waveform that's used to drive the beam across the screen and then reset it and drive it across the screen again is a continuously running sawtooth oscillator. Okay? So it just keeps going along. And you'll see, typically on those types of scopes, you'll see controls like this, where the horizontal or frequency selector, you see it's kind of arranged. See the dot is, in this case, is between, say, 1 kilohertz and 10 kilohertz, or 1 kilocycle and 10 kilocycle. Okay, and then there's a vernier control to kind of adjust you in between. But it's really kind of uncalibrated. But it's saying approximately, you know, somewhere, if I have this set to about 30, and I'm sitting here, it's probably about 3 kilohertz is the rate at which I'm moving that across, 3,000 times a second. Okay, but it's really kind of an uncalibrated thing. It's just kind of moving that across, and it's just a continuously running oscillator. Okay. The problem with that, number one, is it is uncalibrated, so I can't make precise timing measurements. Okay, but I can look at relative wave shapes, no problem. But I can't really make precise timing or frequency measurements by looking at it. The other problem with that is that because it's a continuously free-running thing, if I want to look at a waveform, okay, an input, you know, usually that input is not going to be synchronized to the sweep speed. And the waveform looks like it's rolling back and forth or swinging back and forth. It's kind of a big fuzz across the screen. It's not locked like we're looking at right here. Okay, because the horizontal sweep speed is not necessarily going to be exactly the same or harmonically related to the signal that you're looking at. So the way these types of scopes got around that is something called a sync control, synchronizing control. And so we have this horizontal sawtooth wave that's being generated to move that beam back and forth. So we call this the sweep, and then the retrace, right? The retrace is zooming back and forth and retracing back with steps to go back and do it again. But in order to kind of try to lock that thing to the signal you're looking at, so you can kind of stabilize the waveform to see it, what these circuits would do is have a sync control, which would take a piece of the signal you were putting in and inject it into the oscillator that's creating this, to try to do an injection lock, to try to lock on some harmonic of that signal to kind of make it somewhat stable. Okay? And it kind of works. So if you played with the sync control and you adjusted the vernier, you can kind of get to a point, oh, okay, I got a stable waveform, you love it. Okay? But everything's kind of uncalibrated. It's just a kind of a way of giving you a stable display so that the signal's not sliding back and forth across the screen. Okay? But that was the technology, you know, with the early scopes and with some of these service grade scopes, was this recurrent sweep. It was an easier thing to do, and it was really what the technology allowed at the time. Okay? So the Newline scopes were like that. There's like a 304 was like that. Of course, the later ones all became trigger sweep, and that's really where we are now. And what most of these scopes are here now are called a trigger sweep scope. Now the difference is we're still generating a sawtooth wave to zoom or sweep the beam across the screen and retracing it back. But the difference is it's not free running really. What's going to happen is it's going to sit there waiting with the beam over on this side until something kicks it off. Okay? And what kicks it off is something called a trigger. Okay? So a trigger sweep scope will only sweep when it gets triggered. So if we tell the trigger circuit, which we're going to talk about in a bit, whenever the voltage gets to this point, shoot the beam across. So if you've got this repetitive waveform, each time it reaches that same spot in the waveform, we're going to shoot the beam across. And guess what? We get a really nice stable display because the sweep is sent across the screen at the same point in this waveform each time it comes back around again. So it gives you a very, very easy way of synchronizing and getting a very stable display without trying to harmonically match. The sync control is one of the dead giveaways, although I should say that some manufacturers might call trigger sync. Okay, but usually, most of the time, you'll see it'll have trigger controls as opposed to a sync. And then really the giveaway is the sync control. A lot of times, like this one here, it's a vernier control. It's like how much of that input signal am I going to inject into this horizontal circuit to make it lock? You don't have that vernier control on sync for the trigger sweep scope.
I would think in solid state scope, you know,
Yes.
all will be all triggered, I would think.
The vast majority is, but not all. Okay, but the vast majority will be.
What about your old Tektronix, your 545s and 535s?
All triggered sweep scopes. Tektronix pioneered and kind of invented,
Yeah,
I would say they invented, they certainly perfected the triggered sweep
But
scope.
doesn't that have a sync on it also?
I don't remember that one specifically.
Continuous one sweep, right?
I'm sorry?
On the scope, it's like a continuous one sweep.
Yes, so what that kind of gets into is the trigger mode. We'll talk about that, where if in the absence of a trigger, it'll send the sweep anyway periodically, so you don't have to, if you don't get this trigger set up again.
Yes, the easy way on triggered scopes, you have multiple trigger inputs. You'll have something there that says AC or out external, or it's, and also when you get into the older sync scopes, most of them have banana inputs, not CNCs and stuff.
I guess I'd also like to make this comment at this point. There's various grades of test equipment. There's hobbyist stuff, the kit built.
Yep.
There's service equipment, like the guy used to repair TV sets. And then there's laboratory grade equipment. This day and age, when you can go out and buy one of these scopes for $100, there's no sense to use anything except laboratory test equipment.
It just happens to be, if you happen to have
and once Boehm pioneered the trigger sweep, all the lab scopes are triggered.
It doesn't want to shame the outside.
Well, I said there's a recurrent sweep scope over here. I think one of the others I thought over here was a recurrent sweep scope. So it's good to see it so you can recognize it. Another dead giveaway is that the horizontal is generally not calibrated.
Yep.
So if you're out looking for one, you don't have one, things like that, keep an eye out for something that's got some trigger controls. We'll talk about it. They'll typically have a calibrated microseconds, milliseconds, time per division type of horizontal control, as opposed to a vernier and a range switch. Okay. So you'll see the controls in a couple. When we look at some of the scopes, you'll see some of the different types of controls. You'll typically see sweep time per division. Now, what this tells you is not how long it takes the beam to get from one end of the screen to the other. All right, it's how long it takes for the beam to reach each division as it goes across. So if you see something here, it says, say, 2 milliseconds per division. That means it takes 2 milliseconds to go one of those divisions, and you've got 10 divisions across the screen, so it would be 20 milliseconds to go completely across. Okay. Also, a lot of these scopes will also have a variable control in the middle. Usually it's in the middle concentrically with the switch. And typically dialed all the way to one end. You see where it says cal down here? If you dial it all the way, it kind of clicks. Then you're in that calibrated mode where you can actually leave those numbers. When you turn that off of that click and turn it down, it's like a vernier control, so you can make a variable sweep speed. It's not calibrated at that point, but if you're just looking at wave shapes, it might be useful to do that. And usually that vernier control is enough. If you dial it all the way down, it's the same as dialing down at least to the next lower step. Okay? But if you want to use them to make some calibrated measurements, if you want to measure the period of a signal, so you can do 1 over that to measure frequency, you've got to be in a calibrated setting. Right? So you can say, okay, this signal takes 3.2 microseconds to go through one cycle. You can do 1 over that to calculate its frequency.
The timing circuit on that is an RC circuit?
It's not an RC, because an RC is non-linear. Right? An RC circuit, if you look at it...
RCL then?
No, not really. What they typically would do is use what's called an integrator, where you have, in effect, a constant current dumping into a fixed capacitor. Okay, so if you have a constant current dumped into a fixed capacitor, over time that voltage builds linearly. Okay, whereas an RC, when you turn an RC on, okay, then it's kind of jarred, and you get that exponential type of response. So that wouldn't give you a linear sweep. We want a linear sweep. Now you could play games with RLCs to get something somewhat linear, but if you're trying to adjust from seconds per division to microseconds or picoseconds to a division, it's very tough to build up all those RLCs to make them all match. It's a lot easier to change capacitor values and current source values to get these various changes of linear sweep.
Why don't they just use a computer clock?
Well, the new scopes don't have this anymore. Right? The new scopes are just sampling over time.
The question I was trying to ask is that when you get an older scope,
Yep.
do you have to worry about the possibility of capacitors losing their capability and therefore your timing goes off?
Absolutely.
Is that?
Yeah, so it's typically, the timing will be controlled generally by, it will be controlled by R's and C's, but not in a simple RC circuit.
Right.
The R's would be used to adjust the current that's going to be applied to a fixed capacitor. There might be different capacitors that get switched in. There might be different resistance values that get switched in that controls that current. Okay, and it very well could be that some of those might have changed value and changed the calibration of that. So absolutely, it will.
Yeah, when you get back to that sweep time per division control for a second, remember what you said in the inner pot, you could adjust for, let's say, it's almost like ignoring the fact that you have a trigger scope and you're just kind of looking for waveforms and wave shapes. What I'm saying is that adjustment, is it irrelevant to the setting of the sweep time per division?
Yes, it is.
So in other words, wherever you've got it, if you've got the pot off of the detent where it's switched off,
Yeah.
then you're not using that sweep time per division control.
You're somewhere between it and the lowest value. Let me show you the example here on the scope. So look at the screen here. So if I set this up here, this thing kind of focuses. We can kind of see this is going at 10 microseconds per division. Okay? If I take my variable, you can see I can actually adjust this and go slower. This particular scope will actually show me a calibrated value. Okay, most scopes don't have the on-screen display, so you don't know where you are. Yep.
We have a time warp generator back here that will make a little.
Okay, yeah, so there's an example that we'll be able to use to go look at that. And you'll notice I can adjust this all the way down to 30 microseconds of division, and if I go back up to where I calibrate, if you listen carefully,
Nice. Oh, even that.
click, okay, now I'm in the calibrated position. Okay, so this would go 3 times down.
Go to a faster sweep, because a lot of times what you're trying to do is fill the screen with a waveform and get a whole
Yeah, so you can adjust this down and go see. So you can see, right here I'm sitting at 1 microsecond division. There's 2 microseconds of division. If I go back to 1 and I do my vernier adjustment, you can see I can go down past 2 and even further. But in most scopes, that's going to be an uncalibrated mode. You don't really know what the sweep speed is. It's really just a matter of adjusting things to get a waveform shape that you want to look at.
Yeah, sometimes you don't want to look at 2/3 of a sine wave.
Right, yeah. Okay. And if you don't really care, or you know what the frequency is, you don't care what it is, you just want to get the right, a certain number of cycles on the screen that might get, kind of fill the difference between the discrete steps you have on the, both for the horizontal display now. Yeah. Look good?
Yeah.
Okay.
I want to ask you one question.
Sure.
At my age, you forget, you know, you wanted to ask a question and you forgot the question and then it comes back to you and then you forgot it again.
Well, ask it now, let's go.
The question is, one time I instructed some people at Tasty Cake and I took the scope out and I was showing them how to use the scope.
Okay.
And unfortunately, it kind of goofed because we were looking at a Y, three-phase Y line.
Okay.
And, unfortunately, I just thought that I could just put the
ground
on the center of the Y and go to the outside. Well, that was a dumb move because it burned the sound.
Yeah.
It burned the wire on the scope and I had to replace it. But how do you do something like that?
Well, this is where you've got the scope when you plug it into the outlet.
Yeah.
It's grounded.
I don't want it grounded in that case.
Yeah, so there's two things you could do. There are scopes that are rated for floating operation, where it might be a battery-powered scope where it's not ground, and then you can kind of make the ground of the scope anywhere.
Right.
But then you've got to be very careful because it's a dangerous thing to do, because if you clip to something, say, this is ground as far as the scope's concerned, it may not be ground with respect to what you're sitting on or other things you're touching. So you get into this very dangerous situation.
Well, that's why they're plastic.
So, right, exactly. So, but you also have to be sure you're not touching anything or touching the ground on the scope.
Well,
Usually what you're going to do is, in all cases for what you're doing in your lab, always try to be sure that you got the scope grounded, and if you've got a hot chassis, you're going to have to use an isolation transformer or something like that, so that when you make that ground, you don't short anything out. Okay, so you've got to be very careful whether or not, because especially with some of these older sets, you can kind of plug them in either way, so the chassis is hot or not, depending on which way you plug the thing in.
You will find a lot of these inexpensive signal generators and scopes that are grounded are not compatible.
Yep. Yes. So you got so you're really, if you get into the habit of putting polarized plugs on your things, so they always go in one way and everything's kind of always grounded, is always a good thing. Isolation transformers when you're not sure. Yeah. Something you don't have to worry so much about with a voltmeter because you control both ends of that. The scope you control where the ground gets connected, but even if you don't connect it, you're still connected to ground through the line.
So when we're doing a measurement like that, we just touch the probe tool without hooking the ground up.
Well, you still, you can, but the problem is now your ground connection is through the AC line. And if you're working on very low frequency circuits, sometimes that's okay. But you can pick up some noise, you can get, those kinds of things. It's always good to be able to have a local ground to connect to. It's always a very much safer thing to do as well. So isolation transformer connected to ground. Now you force the chassis to ground, and you don't worry about leaning your ground when you got the probe in there.
I'm the ground once already.
Yes.
Well, even though your ground is, even though your neutral is grounded back at the box, you could have a potential difference.
Absolutely.
Down the line.
And like this gentleman was saying about this high-power Y circuit, that's where your 2-input scope with invert and add lets you make a differential measurement.
Yep, absolutely. Yep. Okay, so again, I brought this up because this is the biggest difference you'll see between kind of the service grade scopes. Some of the older things won't have the calibrating thing. Also, those same scopes that have got the kind of recurrent sweep, usually those are the ones that don't have a calibrated vertical input either. Instead of having a volts per division control, a lot of times they'll just have an input attenuator that says 1x, 10x, or 1000x, and some vernier gain control. Okay, so you won't have a calibrated vertical, you don't have a calibrated horizontal. Okay, but that's another way to kind of view that. Do I have something that says volts per division, or do I just have something that says input attenuation? Okay. So let's talk a little bit about triggering or synchronizing. Why do we want to do that? All right, we want to do that so that the waveform we're looking at, we can actually visualize and see. okay? If this guy was not triggered, I'm not triggered, I can't see that waveform, right? It's just kind of going back and forth, it's not synchronized to the trace. I can go play with the vernier here and maybe kind of lock it on if I'm really careful, kind of, you know. This is the game you play with the old recurrent sweep scopes. The sync can kind of help injection lock and kick the oscillator at the same time to try to lock them together, okay? But it's tricky to try to do. So what the trigger does, okay, let's go adjust it and trigger this thing, boom. Okay, what the trigger now does, okay, it says, okay, I'm going to kick off that sweep at a particular point in the waveform. Okay, that's why we trigger, so we can stabilize a waveform on the screen. Okay, the recurrent sweep scopes try to lock the sweep rate by injection, kicking the horizontal oscillator. Okay, the trigger sweep scopes literally kick off the sweep at a particular trigger location in the waveform. Now, what we can think about that, let's say this was how my voltage was varying versus time. Okay, I could set up a trigger point to say whenever the voltage reaches this point, that's when I kick the sweep off. So that I'll sweep and see this portion of the waveform. The next time it occurs, look at it again and again and again, and it just overwrites itself, and you get a nice stable waveform on the screen. All right, so why do we want to synchronize your trigger, right? We want to stabilize that waveform on the screen so we can see its shape, make some interpretations of what's going on in the circuit. Okay. So again, the recurrent sweep scopes got a sync, and that's the thing that takes a piece of that signal and tries to injection lock this free-running horizontal oscillator, kind of force it to lock and run at the same speed. The only control you have is this sync control. It's the only thing you have. Yuck. Yuck. You know, it's usable, but if that's what you have, use it, and they work fine. It's not calibrated. You kind of have to play with it a little bit, but that's what it is. What it is. The trigger sweep scopes, a lot more controls. Okay, to control what we're going to trigger on, what aspect or characteristic of the signal we actually want to synchronize on. And we'll talk about some of these controls. You'll see a slope control, a coupling control, a source control, a level control, a couple of different things going on here. We'll talk about those. Because, again, this is the thing that will trip most people up when you sit in front of a scope. It's like, well, why can't I see something? I have no trace at all. Where'd the trace go? Why don't I have a trace? Or if I have a trace, it's not, you know, it's not locked, it's moving all around. Most of the problems we'll kind of get into because we're not triggering right. Okay? So that's why I want to spend a little time talking about that. The good thing about the old recurrent sweep scopes is you always had a trace. Right? If you couldn't use it, we always had it. Okay? That's right. The trigger sweep scopes, okay, you can set them so you'll always have a trace. But once you get familiar with how to use triggering, you can always get a trace you can actually use. Okay, that's the whole idea, right? Okay. So let's talk about some of the controls we have on a trigger. So we have our trigger source, right? What does that mean? What's the source of what are we going to trigger on? Okay. Normally, most of the time we use what's called an internal trigger, which means it's going to pick off a piece of the signal that's coming into the scope internally and trigger on that portion of that input signal. That's what the internal means. Okay. There's also an external trigger, and what that means is that there's also a connector on the front of the scope that says like an external trigger in. So even though I want to look at this waveform, maybe I want to look at that waveform synchronized to some other signal. Right? So I can probe that other signal, bring it into the external trigger in, and then look at the other signal with respect to that. Okay. Again, that one and the line trigger are two you probably won't use that often, but they're there. Okay. But the internal trigger, 90% of the time or more, that's what you'd be using. Yeah.
Could you just give us a couple of real-world examples where you might use the other triggers?
An external trigger? Let's say, for example, an example of that is, let's say we're going to be using the scope in an alignment situation. Okay, let's say we have a sweep oscillator that we're used to inject a signal into an IF, okay, and sweep its response to see when we've got the thing aligned. Most of those sweep oscillators will have a synchronizing pulse that each time the sweep starts, it puts out a pulse, right? We can take that pulse out and bring it to the external trigger input, and now when we're probing, we'll be able to each time the signal, the sweep goes across, it's going to be at the same frequency out of the sweep oscillator. So as the scope sweeps across, the frequency from the sweep oscillator is also sweeping across. You can literally trace out or see the response of the IF as you're tuning it around. So that's one example where you might use an external trigger to trigger on some aspect of something else. Or it's a big synchronizing waveform to some synchronizing pulse or something like that. Okay. So let's talk about trigger mode. Okay, so I'm going to trigger on something, usually a piece of the input signal. Or maybe it's from channel 1 or channel 2 or something like that. The trigger modes, most of them will have an auto mode. That's the one usually you're going to start at. Because what the auto trigger says is that, okay, I've set up the trigger, I want to trigger on channel 1 with these characteristics, but if for some reason those trigger settings are incorrect or the signal's not there, the scope will send a trace periodically anyway. Okay? So it will kind of automatically trigger itself, even in the absence of a valid trigger signal. That kind of means you'll always have a trace. Okay? So that's a good thing. Okay? The normal trigger mode is one where you only get a sweep if you get a valid event that satisfies your trigger criteria. Okay? So it's good to start with auto, okay? Because you always have a trace, you'll see really what's going on. If nothing's going on, or you're not hooked up with something, it helps. So that's usually where you want to start if you have an auto mode. Yes?
So in a sense, that sort of imitates a recurrent sweep scope.
Exactly. It imitates a recurrent sweep scope in the sense that you'll always get a sweep, but if you do get a triggered event that meets your trigger criteria, it will then literally trigger on that, as opposed to try to injection lock to it. So it is essentially the functional equivalent of an untriggered recurrent sweep type scope. Exactly right. Okay. There's also modes for doing a single trigger, which means I set up the scope and then I get an input signal and it's going to do one trace and stop. Well, what good is that? Okay. For what you guys are doing, not good at all. Okay. Where that was used is when you're looking at like the response of a circuit to one particular event. Usually the writing speed of the scope is so fast that one sweep you wouldn't even see it. So where that would be used, like in design labs and things like that, is maybe with a camera on the front, okay, a street camera or something like that, so that one single event would be captured by photographically, and then you pull out the film and look at it and that kind of a thing. But for what you guys are doing, a single sweep, a single trigger, you almost never use. Okay.
You've got a whole generation of people that never saw a Polaroid scope camera.
So have you ever seen them? They're basically
died by those things
yeah.
before digital scopes.
Absolutely. In fact, one of the rites of passage, when I got out of college in 1985, I got my first job, or in the lab, one of the rites of passage was to take the Polaroid scope camera and have your picture taken with it. Now these scope cameras look about this big. Now, you see a lot of these scopes have a groove on the top. The camera would actually hang on the front of the scope, cover the whole thing up, and a little Polaroid pack behind it. And then you can open the shutter or do a time shutter or whatever. But they were focused looking at that. So if someone took the scope camera, stuck it in your face and took your picture, and when you developed that picture, it was like a big nose, and eyes way back here. And it was typical Polaroid film, and when you pulled it out, it would kind of curl up. But taped up on the wall over the lab was the scope camera photo of everybody who works in that lab. but yeah, you're right. We live and die by those things. A little 10-pack of film you stick behind them, but that's where you typically use things like single channel, single sweep, I should say. Now some of the scopes you'll see have a special TV triggering mode, which allows you to trigger on the horizontal or vertical sync pulses of like an NTSC video signal. So we've got an NTSC signal generator back there, so you can actually play with some of that. But that's what the TV trigger. Not all the scopes have that. It was an option on some scopes. Also now, so we know what we're going to trigger on and how we're going to trigger with respect to that signal, whether we're going to always trigger or whatever. But now we'll talk about coupling. Okay, same reason we use coupling on the vertical channel on the signal. We're also going to determine how that signal gets coupled into the trigger circuit. We can do an AC or DC coupling. Most of them will at least have that. And some scopes will have other things like be able to reject high frequencies or low frequencies and things like this, different filters. Okay. But usually AC or DC coupling are used for the same reasons that we would use them on the vertical channel. Okay. To eliminate the DC component, to just trigger on the little wiggle that's sitting on top of the DC. They might use AC coupling, or we want to trigger at a particular voltage level, DC voltage level. Okay, so we'll see that. Okay. Also, we're going to see some controls for trigger level and slope. Okay? And the way to think about this is the slope is usually positive or negative. Okay? And then there's a voltage threshold of the level. So this is kind of typical of what the controls you'd see. You'd have a level control that can go plus or minus. Okay? And you've got a slope control. So in this case, if I've got the slope set to positive and the level set somewhere positive here, We're going to send this sweep off when this voltage that's swinging back and forth crosses that threshold right there. Okay, that's kind of set by this. If I adjust that threshold down, right, then I'm triggering because it's coming up through that voltage down here. So that's essentially adjusting a threshold. Okay, to say when that voltage reaches that threshold, that's what I want to shoot the sweep across. The slope, positive or negative, says which way am I approaching that threshold to cross it. Am I approaching it from the bottom and crossing it and going positive? That's the positive slope. Or am I approaching that voltage threshold coming down, and I want to trigger when I go down below that threshold? That's the negative slope.
Well, how do you know exactly where you're triggering? Say you take positive slope. Now you say you want to set the trigger threshold. How do you know where on that gradical you're triggering?
You just watch it.
You watch it. Okay?
Oh!
Yeah, so if we look here, the difference between this and this, you see this one's down here, this one's up here.
Okay.
Let's look at it here.
Okay.
Let's look at it here.
I see.
So if I look here...
There's no little intensified dot that shows you.
No, the newer digital scopes actually show you an actual voltage threshold. Here you actually watch it, yeah.
Make the waveform. Make the waveform.
Yeah, so let's do it here. Let's actually, let me turn the amplitude of this up a little bit. And I'm triggering on this waveform right here, okay? And if I adjust the level, let me turn the level to, no, so it's not on auto. And so if I adjust the level, you see how my starting point of the waveform is moving up or down?
Okay.
And if I change the slope, now I'm triggering on the negative side as it's coming down, okay? If I trigger on the positive, okay, now I'm triggering on it going up. The thing you will generally have to play with is the level. Slope, positive or negative, usually won't really matter for what you're doing unless there's something specific you want to look at. Okay? So, but the level is a thing you might want to play with. That's going to be the most often used control in the triggering. Get the source right, get the coupling right, get the level right. Okay? But that's kind of the effect of doing that by triggering on positive or negative and either a higher voltage threshold or a lower voltage threshold. Okay? So and it's all kind of relative, right? There's no absolute values that typically that we're putting in here. It's just kind of relative. Okay? So we'll talk a little about probing. I want to make sure everybody's kind of clear a little bit on triggering because there's a lot to it. It's something that you got, that's the thing to play with a lot because you really understand kind of what the scope is trying to do. And the whole idea is just to get the sweep to kick off at a particular location in a particular waveform. In many cases, you don't really care where it is as long as it kicks off somewhere. Okay? But you have some controls between the polarity, or I should say the slope, which direction the signal is going when it crosses the threshold, and what the voltage threshold is. Okay. And then you've also got the coupling controls and things like that that can help you out to isolate a particular portion of the signal to trigger on. But in most cases, like an AC coupled trigger, set threshold near 0, you get a trigger. Okay, kind of a good way to go. So I want to talk a little bit about probes. Okay, why do we use probes? Okay. Well, obviously we want to connect whatever we're working on to the scope, to the input channel. So we want to look at the voltage. We talked a little bit about loading, right? Sometimes we've all worked on circuits where you touch the probes and whatever you have, whether it's a meter or whatever, to your circuit, all of a sudden your circuit does something different. Okay, that means the loading of that is creating a problem for the circuit. It can't drive the load that particular device presents to it. Same thing can happen with a scope. We mentioned that, remember we talked about the scope input impedance. Most of these scopes have got a 1 megohm input impedance with about anywhere from 10 to 30 picofarads of capacitance. If you hang a piece of coax on that, 3-4 feet long, that would be another 30 or 40 picofarads of capacitance. Okay, so now all of a sudden you're looking at 50 picofarads of capacitance or more kind of being put into that circuit when you touch. You take a piece of coax out the clip leads and clip it onto your circuit. Okay, you might have just added 50 picofarads of capacitance to that. Well, does that matter? Well, 50 picofarads of capacitance at 455 kilohertz is a few k ohms, right? Well, will that matter? Depends on the plate impedance of, like an IF amplifier or something, right? Whether that would matter or not. Okay. Here's a typical probe. Okay. Now, one of the probes you can have is a typical, just a passive probe, which really is nothing more than a wire that's connecting the input to your scope. And you can have these problems with excessive capacitive loading and that kind of thing. Also, typically the 1 megohm doesn't bother too many circuits, but the capacitive loading does. So that's one of the reasons why you start seeing probes called 10x probes. Okay, 10x probes They don't magnify the signal by 10x, they actually attenuate it by 10x. So it could be a little bit deceiving. It isn't really an amplifier, it's really a 10x attenuator. Okay? And we'll talk about why we do that. But that is the most common. 1x and 10x are probes are the most common things. If you're typically looking at like audio circuits or low frequency stuff below 1 megahertz or below a couple hundred kilohertz or less, sometimes you don't need probes. Okay? Sometimes you do. Okay? But yeah, something to think about. But the scope, it looks like a 1 megohm resistor to ground with some capacitance to ground. How is that going to affect what you're looking at? Okay? So it may determine whether you need a probe or not. There are all kinds of specialist probes too. What you're looking at, there's active probes that actually have a little amplifier right in the probe tip. Okay? So very, very little loading to your circuit, but they typically require a power supply and things like that. There's current probes, there's high voltage probes. Yeah.
I've got an old probe set from one of my older oscilloscopes. Has an RF demodulator probe and a, I can't think of the other one, I just had it in my head a second ago. But it's got a couple different probe types with it. Would they still be useful with the newer?
The answer is most likely.
Okay, so I'd want to have one of them.
Absolutely. Now the RF demodulator probe is really nice, especially for doing radio alignment, because what the RF demodulator probe is it's essentially an amplitude demodulator. It's basically a diode and a capacitor. And what it allows you to do is, say you're looking at a 455 kilohertz IN, okay? If you probed it with a direct probe and you went fast enough in sweep speed, you actually see 455 kilohertz. And if you went slow enough, you could actually see the modulation of that 455 kilohertz in the IN. But what you really want to do sometimes is just look at the magnitude of that, rather than the envelope of that. So an RF demodulator probe will trace out the envelope of the RF. Yeah. Okay, so it's an AM detector. Is really what an RF demodulator probe is. It's an AM detector.
The other one I have is a crystal probe.
Same thing.
Okay.
A crystal probe is essentially an RF demodulator. So it might have different frequency range, but it's basically the same thing.
I'm sorry, can you just repeat, what part of, let's say, an RF circuit would you want to use that demodulator, that probe that you know?
It's when you want to look at the magnitude of the RF signal itself, rather than looking at the RF cycles.
The place they really get used is if you're doing sweep alignment of a circuit.
Yep.
And especially in the old days when you had scopes that didn't have the high frequency response to actually measure the RF.
Yep.
So you go in with a detector probe, and now you're, like you said, you're measuring the amplitude, the magnitude of the thing.
So you're not going to see, let's say,
No, you won't see that. You'll
the envelope.
it's like the DC we were looking at on the radio.
Well, let's take that example. Let's say you're using a sweep oscillator to do some alignment. Okay. A sweep oscillator, I'll just kind of let's take it. What it does is changes its frequency versus time, right? So as time goes on, we get higher and higher in frequency. So we might start off at a low frequency, and then we go up to a much higher frequency at the end, and then it starts over again. Okay. So we could say, well, I'm going to sweep through this thing, and maybe somewhere right around here, I'm at 455 kilohertz for my IF. Okay. If I looked at the output of the IF on a scope, okay, just the IF itself would look like, if I swept it up fairly, let's say this is sweeping, once per second or something like that. So if I was sweeping along to look at 1 second, this 455 kilohertz is going so fast, I just see the envelope of it, right? And it just looks like fuzz. But what will happen is, as this thing sweeps through the passband of the IF, the magnitude of this envelope, let's kind of draw it like this, the magnitude of this will kind of peak up and then come back down again. So the envelope will kind of look like this, right? And this will just be filled in, because that's 455 kilohertz oscillation, and the magnitude of it, we're going to get a bigger response when we sweep through the center of that. Now, a lot of the scopes didn't have the bandwidth to be able to pass this 455 kilohertz.
Well, or especially if it was 10.7
or 10.7 megahertz.
Or 21 in a TV set.
Where, yeah, so the IS, on a high enough frequency that you can't respond to that, how do you use the scope? What you do is simply amplitude detect that envelope. Okay, and the simple schematic for that is a simple diode feeding a capacitor, right? A little bit of resistor bleeding it off, right? So now we're going to basically just pass the higher peaks are going to charge up that cap. They get discharged here. Each cycle we recharge it back again, and we wind up just tracing out this response. So the output of this circuit will just look like this. Okay. So now we were able to sweep the circuit this way, synchronize the scope to that sweep, look at the output of the IF, and when we're tuning it, we'll actually see the IF move around and actually peak it up and get its response.
Yeah, that's how you're aligning the IF.
Exactly. Yep. Exactly. So it's kind of like what you do when you're doing your alignment now to peak things, but now you can literally see the shape of the skirts, the filter, where if you potentially injected a signal that was off frequency back and forth, you could manually trace this out. This will allow you to actually literally see it on the scope. Make sense?
Yeah,
I guess
it does.
I'm sorry?
I guess I'll hang on to them then.
Absolutely. They're harder to find nowadays, so it's actually a good thing to have.
Can you just build a probe like that with a germanium diode?
Sure, absolutely. Sure.
And you don't have to worry too much about matching the capacitance to your scope?
Yeah,
Tuning it?
No. They're pretty simple to build.
Okay.
A little 1 in 34
And all
or
you need
something
is a
like
good
that.
sweep generator and you can do this.
Yep, absolutely. Okay. So that's one probe I probably should have listed on here. It's a really good probe. If you ever see someone who's got a crystal probe or an RF detector demodulator probe, it's a good thing to have. Yeah.
That's the irony you find is it's old scopes at Handfest for $5 because that's what they have with them.
Yeah.
And that's why they're worth picking up.
Yep, absolutely. Okay.
Yeah.
So let's talk about why we would use probes in other circumstances, especially 10x probes. What are they? Why we use them? And what are the considerations for using them? Okay. So a 1x probe is simply a direct connection to the scope input, right? And it can have excessive capacitive loading because of the coaxial cable, 15 or 20 picofarads per foot or whatever it might be, the coax that you're using. So you add all that up, and you can throw a significant amount of capacitance down on a circuit which it may not be so happy with. Okay, so that's a problem. So a 10x probe what it does is it isolates the capacitance of that cable and the scope input from the circuit with a series resistor. Okay, the series resistor in most cases is a 9 megohm resistor. So the scope the circuit sees 9 megohms before it sees that capacitance. So it doesn't really see that much. Okay, so it isolates that, so essentially you don't load the circuit as bad. Now it sees, from a DC standpoint, it sees 9 megohms plus the 1 megohm to ground of the scope input. So DC-wise, it sees 10 megohms instead of 1 meg. Okay, we've reduced the loading there. And it also reduces the capacitive loading, okay, by isolating it through this 9 megohm resistor. So you will be less likely to affect your circuit by probing. Yeah.
If you knock your signal down by a factor of 10, do you gain 10 times of the advantages, or do you get more somehow?
It depends on the circuit you're looking at, because some circuits are very insensitive to the loading anyway. So the answer is you generally gain a lot more than you give up. Okay. The only problem you can run into is if the signals you're looking at are so small to begin with. If you knock them down by a factor of 10, then they're really small. Okay. But in most cases, especially for what we're working on, the signals are large enough that the 10x attenuation of the probe is not a big deal. Okay? So, although the scope input attenuates the signal by 10x, because it's 9 megohms in series with the 1 megohm, the scope sees what's across the 1 megohm, right? So you get that 10x voltage at the bottom. Okay? So the good is you reduce the effect of the capacitive loading on the circuit, and you also reduce the effect of the resistive loading because you've increased it by a factor of 10. The bad is you need compensation. So how many people knew you needed to compensate your 10x probes? Okay, a couple of you.
Yeah, but how many knew what that meant?
Well, let's talk about that, because it's probably one thing that is the least understood thing, and people don't care about it. They don't know what it is. So let's talk about what it is. Okay. So here's schematically kind of what that probe looks like. Okay, so I've got my probe tip and the ground lead that I connect up to my circuit. I've got this 9 megohm resistor here. Okay. And then the scope's resistance. Now the problem is that we still have some capacitance from the cable that's connecting the probe. We have some capacitance at the input. So what's going to happen is this resistor, let's ignore that guy, this resistor and these capacitors form a RC low-pass filter. So that now all of a sudden this probe is frequency dependent, right? As I go higher in frequency, this 1 megohm resistance is shunted by those capacitances. Okay, so I'm going to roll off the response of the probe. Well, crap, why did I do this? I did this so I could probe signals that were higher frequency in the first place. So the way you get around that is that in addition to using the resistive divider, okay, for low frequencies, what we'll do is there's a compensation capacitor that's added in the probe that compensates for this capacitance. And it turns out if this ratio is 10 to 1, if we make this ratio 10 to 1, we now have a capacitive voltage divider which is frequency independent. Right? So at any given frequency, the capacitive reactance of those two will track 10x as frequency changes, just like the resistors are 10x at low frequencies. So that now, as we go higher and higher in frequency, the capacitive ratio is going to dominate, the 10x attenuation. Now, because all the scopes have got a different amount of capacitance, they're not all the same. They're all 1 megohm resistive, but the capacitive loading of each scope is different. We can't just design one probe that will work with everybody, okay, or every scope from every manufacturer. So that compensation capacitor is made adjustable. Okay. So now what we can do is there's a way of actually compensating that probe for that given scope to flatten out its frequency response. Because if that capacitor, for example, is too small, what's going to happen is at higher frequencies, you're going to get a low-pass filter. You're going to attenuate the high-frequency signals. However, if that capacitor is too big, you're actually going to peak the high-frequency signals. You're going to have more, less attenuation at high frequencies than the 10x. Okay? So the idea is you want to adjust that compensation capacitor to flatten the frequency response. Boy, that sounds like a hard thing to do. It's actually really easy. Okay? And most of the scopes, when you look at them, have a calibrator signal on them. You've seen them, like on this scope here. I don't know if we want to move the camera over to this scope out. Okay? So most of them have a calibrator signal on them, like that, a little square wave. And the purpose for that is, a square wave is kind of unique, is that, who knows the frequency content of a square wave, right? You have a lot of energy at the fundamental frequency that it's oscillating, but you also have energy at 3 times that frequency, 5 times that frequency, all odd harmonics. So you've got a lot of energy at high frequencies. That's what makes the edges really steep. Okay? So the high frequency component is all in the vertical edges of that square wave. Okay? So by looking at one waveform, we can see if the low frequency and high frequency response of the probe is equalized. And what you'll find is that if the capacitor in this case is too small, you're undercompensated and you're going to round off or low pass filter the edges. If it's too big, you'll overcompensate and you'll peak the edges where the high frequency content is. But when you get it right, you get a nice square wave. So if you look at all these 10x probes, okay, and this one, I don't know if this is a 10x or not.
Yes, it is.
Okay, and it should have a compensation adjustment on it somewhere.
It's the whole barrel.
Oh, this one you twist or you pull? Okay. A lot of the scopes will kind of be like this one here. Okay, I'll pull this one out of here. And it'll have a little screw, a set screw adjustment. Sometimes it's on the probe handle, on the body. Sometimes it's on the piece that goes into the scope. But it's a little compensation adjustment. It's basically a small little trimmer cap. And here's how you use it. So I've got this guy set up here, and he's pretty well compensated. I've got my little screwdriver here. Okay, I'm going to miscompensate this scope, or this probe. So let's kind of do this here so you can see the scope at the same time. Okay, and watch what happens if I turn the screw, if I get it engaged here. Get my reading glasses. Here we go. Ooh, look at that. Okay, now I'm overcompensated. The capacitor is too big. Those high frequency edges have got less attenuation, so that's why they're ramping up and you see it coming down.
Is that kind of like his RC circuit that we're seeing there?
Yep, that's the exponential response of that, yep. Now if I come back the other way, here's undercompensated. Now the problem is if you don't have if you're looking at, like an IF or something like that, you want to actually make an accurate voltage measurement of how big it is. Depending on if the probe was overcompensated or undercompensated, it won't give you the right amplitude. Because you're going to be looking at something at a single frequency. You don't really know whether it was over or undercompensated. A square wave has got a lot of frequency content in it, so you can actually use that to adjust and compensate that probe to make it flat. And now that probe will work over the entire rated frequency range of the scope of the probe.
And when you do this, it doesn't matter the frequency of the square wave itself?
Not entirely. You'll know, since
you can have that at 1,000 cycles per second?
Yeah, the idea is it has to have fast enough edge to have enough high frequency energy. If, however, you don't want it to be like a 1 megahertz square wave,
right,
because by that time you're already at the frequency range where the whole thing would go up or down.
Yeah,
because you notice there was a response time of how it all came down. Right. If my square wave was so fast that it went up and down before that thing settled, then it would be too fast, right?
So is there a typical frequency that you would use for
Most of them are about 1 kilohertz.
1 kilohertz.
Most of them are about 1 kilohertz. In fact, when we look on this one, they usually tell you. This one says it's approximately 1 kilohertz, 300 millivolts peak to peak.
But I think your oscilloscope, it varies with the speed of...
Yeah, some of the scopes will vary with the time base. Some of them are fixed. This one, I believe, is fixed.
Right.
If I adjust the time base, it doesn't really change it. Okay, but the calibrator on some of the scopes will adjust. So you want to do it at a, like we're looking right here at, see, that's 200 microseconds per division. Okay, something, about a millisecond per division, just under a millisecond per division type of thing. That's about what you want to do to compensate the probe. That's typically where that's going to start to matter. Okay, yeah.
Let's say I'm on a flea market. Somebody has some probes. How can I identify a 10x probe? One more time.
Usually, the 10x probe will have, it'll usually say right on it. It might say right on the body that it says 10x. It might say on the handle that it's 10x. And the 10x probe somewhere, either on the body of the probe itself or on the compensation box, will have an adjustment.
Al was offering the Chinese ones that had both 10 and 1x.
Yep.
Switch it out.
Yeah, some will have a switch, might have a switch, so the switch will short out that 9 megohm resistor, in which case the compensation doesn't do anything at that point. The compensation is only in the 10x mode. Okay, so that's kind of convenient where you have the switch, okay, where you can switch it between 1x or 10x depending on what you're doing.
You can't do that unless you've got a square wave node. You can't, like, if you try to let's say set up a scope that didn't have, maybe I'm not sure how this would work, but if you wanted to use an older scope, like the cycles, and you try to do that, what would be the method?
Well, you could, one way is if you have a signal generator, okay, that you're going to probe with, but then you have to adjust the signal generator to a low frequency where, like maybe a couple of hundred hertz, where things are, things aren't, the capacitors don't really enter into it, and then turn it up to a couple of kilohertz, tens of kilohertz, hundreds of kilohertz, and see if the response is the same. And if it's not, then adjust it back.
Well, the trouble is you don't know whether the generators...
you don't know whether the generator's good. You don't know whether your scope is rolling off or is the probe rolling off. So,
Get a square wave generator.
a square wave generator will do it. Okay. But they also do sometimes the scope itself, if the scope has got BNC inputs, it probably doesn't have more than a couple hundred kilohertz of bandwidth anyway. Okay? I mean, it's got the banana jack in it. If it's got BNC inputs, then it's probably something you'd want to compensate probes with. Okay?
It's irrelevant.
Okay.
Also, the probe may not work with that scope. There's a range there, so depending on how which capacity the input is.
Right. Yeah, some of the scopes will tell you they can compensate, scope inputs from 10 picofarads to 20 picofarads or something. Sometimes they say it, sometimes they don't. So you don't really know for sure whether it will work. But bottom line is, even if it can't be compensated flat, it can still be used to look at waveforms. It just means the amplitude may not be right at high frequencies. In some cases, does that matter? No. Right? You just want to look at the wave sheet.
So the price is right, take a chance.
There you go.
Are the Tektronix probes pretty universal, going all the way back to the tube-type scopes? I mean,
they're fairly, yeah. The difference is primarily the compensation range. Because the older scopes will have generally higher input capacitance than some of the newer scopes.
Okay.
So they may or may not be able to be adjustable that far. Okay. Something else that's kind of interesting, you have to remember this though, if you're using a 10x probe and you hook it up to your scope, if your scope was set to 100 millivolts per division and you hook a 10x probe to it, now it's 1 volt per division. Right? Even though it still says on the dial, right, 100 millivolts a division. So you have to kind of remember that. Okay? Some of the scopes, like the 465 and some of the other kind of more lab-based scopes, use a feature that's on a lot of these scopes, a lot of these probes, this little pin that's sticking out on the side here. You may have seen that on some of these 10x probes. Not all of them have it. What that is, that's a little sensing node that when you hook it up to the scope, it tells the scope, hey, this is a 10x probe. Okay, and notice what happens on this scope here. You can see my volts per division dial is lit up right here. This one has a dual dial. If I pull this probe off, see it move to the other side?
Yeah.
So that's the 1x side. Okay, and when I hook the probe up, it knows this is a 10x probe, and it adjusts it. What did I do? I know, I knocked the coupling. There we go. So it knows that it's a 10x probe and adjusts the scale automatically. Okay, a lot of the scopes will not have the little sensing ring around the BNC to do that for you. Okay, so you've got to take that into account when you're plugging your 10x probe in, that you've just increased your volts per division by a factor of 10. Okay, like even that little digital scope on the corner there, it's a Tektronix scope, but it doesn't have the sensing ring. You have to go to the vertical menu and tell it there's a 10x probe attached. Okay, for some of these other scopes, you just have to know mentally that you did that. Okay, this particular scope here, the readout is on the screen and it changes automatically when you attach the probe. Okay. There are also 100x probes, okay, that would do a 100x termination, typically for higher voltage applications. But the compensation is really the key if you want to make accurate voltage measurements at higher frequencies with these 10x probes.
The other thing we didn't touch on with probes is they're shielded. So that's a real advantage over just sticking a wire in the scope. And,
yeah. Absolutely. So, because it is a piece of coax, right? Now, one thing you'll notice, okay, I've got this long ground lead here. Okay. If you're working at, a couple of megahertz or less, that's okay. But if you're trying to look at something at maybe a 20 megahertz IF, that looks like an inductor at 20 megahertz, right? So this probe may not be appropriate for 20 megahertz because you're going to add inductance in the ground path. So you might go to a probe that has a shorter ground lead. Some of the probes, if you look at them, you look at this one for example. If I yank this tip off of here, okay, I can see I've actually got the probe tip, and then there's a ground or right around there. There's actually little adapters you can plug onto that will give you a very, very short little ground right next to it. So you can probe right down in and have a very low inductance ground path, so you don't get any inductance in that path. Okay, because that will change the frequency response of the probe. For most of what you guys are doing, you'll likely not run into that, but those are the kind of things, you don't want to have a ground lead that's 3 feet long. Okay.
And truthfully, I would think when you're working in radios,
Really high frequency?
There you go. Yep. So here's a probe adapter. This probe tip actually has a little, you can actually put a socket on your board, solder it in, and then this flips right onto the probe and you can connect right up, and it's like connecting the coax right to a coaxial connection right there. Very, very low ground inductance with something like that.
But I think tube radios with the high voltages, I tend to like to use it times 10. Only because I'm not feeding 600 volt B plus into my oscilloscope.
Oh yeah, because some scopes can take that once. You let the smoke out.
It's not 10 volts to drop the voltage down, so you hit the B plus at 400 volts, you're not putting 400 volts in the input.
So again, look at the front of the scope, it'll tell you what the maximum voltage allowable is. Look at the probes, it'll tell you what the maximum allowable is. Okay, so you're absolutely right.
That's one case where older is better.
Yeah.
The old style probe there that you first showed is actually a vacuum tube oscilloscope probe, and it can take about 600 volts. A modern ones can only take about 250. So you may want to actually shop the old stuff for our purposes of NFB radio.
Yes. And also take a look at the front of the scope. The scope will tell you what the maximum safe voltage is. So if you exceed that, you can do it once. Right. You let the smoke out. It might work for a short period of time. We'll let the smoke out, and that's it. Okay. So again, most scopes have got this compensation signal, so you can properly adjust that scope for your probe, or vice versa. Okay. So let's talk about another special mode of the oscilloscope. So up till now, we've considered the scope where the scope itself is driving the sweep. Okay, so it's controlling the X position, sweeping that beam across the screen. Most of the two-channel scopes, the vast majority of the two-channel input scopes, will allow you to go into a mode called XY, where the Y is still driven by the signal you're looking at, but now the X, the horizontal position, can also be driven by a signal you're looking at. You gotta think about it, get your hands on why do I want to do that? Well, you might want to do that because maybe these two voltages relate to each other somehow. This example that I just showed over here, okay, let's say I was doing this with a sweep generator. A lot of these sweep generators, in addition to having maybe a pulse that they put out at the beginning of the sweep to like do an external sync, they also sometimes will have an output that's a linearly changing voltage where the voltage at that point tells you essentially where you are in frequency. Okay? So if I took this signal that's varying like this versus time, and then kind of comes down and resets again at the end of the sweep, if I made this my X signal, driving the horizontal position, and I made this signal my Y, I would get that plot. without having a trigger on it, without having to synchronize, because I'm driving both the X and the Y. Okay? So that's one example.
Now we have that set up, so I can see it, that sweep set up.
Okay, we have it, or we'll set it up. If we don't have it, we can set that up. And we can do a number of different things. If we apply the same signal to X and Y, what are we going to get?
Lines.
You'll get a line, because if that signal would drive vertically this far and horizontally that far, you're going to get a diagonal line. It looks like this.
Yep.
Okay? So regardless of what the signal shape is, whether it's a sinusoid, a square wave, whatever it is, if it's applied to both inputs, you'll get that. Now if there's a phase shift between the two, okay, you can get any one of these different type of wave shapes. In fact, you can actually measure phase shift by applying signals from an input and output of a circuit that's supposed to be doing a phase shift to the XY input, and by looking at these waveforms determine, well, you can't determine the difference between 90 and 270, right? They look the same, right? But because they just look like a circle. Okay, but it's just going to change where things are getting driven. It's something to kind of, you have to wrap your head around and think about it a little bit, but because we're driving both inputs, both the horizontal position and the vertical position with the same signal but delayed in time, you can kind of vary the shape. Now you could kind of make frequency measurements with this. If you have a known input frequency, one input, and drive another one in, by looking at the shapes that you get, many times you can calculate. In this case, I've got a 2-to-1 frequency ratio, okay, between the two inputs. Because one is being driven this way twice as fast as it's being driven this way, so I get essentially 2 lumps, if you will, versus one. Okay, and you can get kind of different ratios. A lot of times these things will spin around. Al's got an interesting thing he was showing over here with the radio, the stereo output. Okay, so left and right channels are ostensibly doing something different. Okay, so if you put them on X and Y, you'll actually see the stereo separation. Okay, where if you put the thing into mono, you get a straight line because they're both putting out the same thing. You go to stereo and you see this kind of. So it's fun to look at, like, what does Led Zeppelin look like? That's why. So that's kind of fun stuff to do with it. I did that with my Dumont scope and my stereo when I was in high school. It's just cool. Turn the lights out and watch this. What are you doing in there? What's that?
There were no chemicals involved, right?
That's right. No, there were not. I was a good kid. I was a nerd. So, but still am. But what can you do? But so that's kind of the fun of XY. But let's really use this to do something. Well, the one example, this example here is kind of shown here, where I've got a sweep generator. Okay. Of course, I picked the wrong font here, so I forget what I even said there. I think it was a sweep generator. Okay. So that's giving me a frequency sweep that's going into the radio I'm testing, and I'm looking at that on the X input. And then that sweep generator is also generating this ramp voltage that's proportional to the frequency as I'm sweeping through. I'm putting that into Y. And now I can literally see the response of, say, that IF that I might be aligning. Okay? Now this is looking at it directly, assuming that I've got a scope that's got enough bandwidth to see that IF frequency, whether it's 10.7 or 455 or whatever it is. This is where if you used an RF detector probe, you literally just see a waveform look like that. Just trace out the positive opposite. Okay. So that's a really nice application. Now, this also shows a unique little thing in here where if you had a little notch filter that maybe put a notch at a particular spot within the sweep, it would give you a response at that point. You can plug that into the Z-axis input of the scope. When we talk about X and Y, what is Z? Z is the brightness or intensity. Okay. So if we put a signal into the Z, we can cause the sweep at that, to get brighter or dimmer. It's like putting a marker on there. Okay, so if I had a notch filter, either a notch filter or a very narrow band filter, I could put a signal into the Z and maybe intensify or blank out at a particular frequency, wherever that notch is. Most of the time you don't need that for doing what we're doing. Okay, if you kind of know where you're sweeping, the extent of where you're sweeping, you can just get rid of that. But the picture I found to put in here had that in there, so that's why it's in there. Okay, I didn't bother editing it out. Okay, so that's one example of being able to sweep or do an alignment by using a sweep generator or a scope in XY mode. Now, if you don't have this ramp voltage output, but you've got that synchronizing pulse, okay, You might be able to set the sweep time. How long does it take to sweep from F1 to F2? It's going to take, 100 milliseconds to do that. You can set yourself to 10 milliseconds of division. Okay, so you'd have 100 milliseconds total sweep time on the scope, and then take the trigger pulse that comes out of the generator and trigger on that, and then so you get the same display, but now you're relying on the fact that you're matching your sweep with the sweep time, rather than driving it directly. So a little bit of an advanced application, but really cool, because not only can you very quickly do an alignment without because if you do it with a voltmeter, you're just looking at the peak voltage at any particular frequency, and adjust the frequency back and forth. You don't really know how well centered. You've got multiple IF filters, okay? You don't really know how well centered you are. Here you'll know whether you're centered. You can actually see the shape of the skirts of the filter, because you're sweeping all the way through it all the time. So it gives you a lot more insight to really fine-tune things sometimes. Okay? But also it will give you some insight too. Let's say I looked at this and all of a sudden I kind of came up and this thing flat topped or dipped down or did something wacky. Might tell you got the gain wrong, an IF stage, okay, or something clipping or something like that. That could add distortion. So you can get some more insight by just getting, if the waveforms are not ideal, you might learn something from that. Okay. Here's an example of an RF detector probe. This has got a DMM on the end, but replace the DMM with your scope, and there's your RF demodulator probe. Okay, that's what you have. Okay, there's lots of different ways of doing it. 1 diode, 2 diodes, things like that. You don't necessarily need the resistor dividers. All kinds of things. The very basic form is like that, right? A simple RC or a diode capacitor. Yeah.
C1 does that decouple? What is that actually doing? Isolating? How does that actually work?
Well, C1 is actually where you're, in some sense, where you're building a charge up. Let's picture what happens here. In this case, with this diode in this direction, positive voltage coming up. Okay, as we come up, it's going to conduct through that diode. It's going to charge on this cap. When you go down, this diode then starts to conduct and build up charge on the capacitor. So when you go back up again, it dumps that charge back onto this capacitor. Okay, so in fact, you can replace R1 with another diode going this way. And it's kind of like a full-wave rectifier, like a voltage doubler. Okay, but really C1 is part of the detector. You could replace C1 with just a diode and go right into this cap and leave nothing here. The problem is now you're DC coupled to your circuit. So any DC bias that's on your circuit will get dumped into this, which you may not want. Okay, remember you're looking at the output of an amplifier. It might be looking at plate voltage. Okay, you don't want that DC voltage to appear across this. So by designing the circuit with the capacitor up front, you've taken away that DC potential, and you're only going to look at the magnitude of the RF.
There's one more thing on that C1. How do you know how big that has to be to do its job for what you're trying to do?
Yeah, that's a good question. It really comes down to what frequency you're trying to measure. Remember, what we're trying to do is use that diode and capacitor and the resistance around it to hold the charge between the peaks of the RF cycle. Okay, so you can kind of figure out the RC time constant of the capacitor and the resistors that are connected to it to say how long is this going to charge up, how much will it discharge from the one cycle when it gets charged and the next cycle when it gets charged again. Okay, generally you're going to find this capacitor somewhere in the hundreds of picofarads type of value. Value is really not that important. If you make it too big, then you might be like a peak detector and it doesn't tail off fast enough. The voltage might go down faster than you can actually track it going down. If you make it too small, it'll discharge a lot between each of these cycles and give you more of a choppy thing. But I mean, literally, there's probably orders of magnitude difference between too big or too small. A couple of tens or hundreds of picofarads to a couple of nanofarads, fine. If you make that 20 microfarads, probably too big. You make it 2 picofarads, probably too small. In between there, you're probably okay. Right? It's really good. There's no rule of thumb. You could look online, and see different designs, use other people's designs, play with it, but there's really nothing critical here. The other thing too to consider though is that if you make it big, its impedance at those RF frequencies you're looking at is going to be very low, and so you're going to load your circuit with whatever's sitting behind it. So you want to make it not too big so that it doesn't excessively load what you're looking at. So as tens or hundreds of picofarads are probably a good place to start. Okay. But like I said, you could look at commercially available designs and schematics and just go play with it. There's really nothing critical about it. Okay. So a couple of so the RF detector probe, if you use that, you'd be able to trace this thing out. So just by looking at the magnitude. So if this was like I said, a 20 megahertz IF or a 10 megahertz IF, and you've got a 1 megahertz scope, but you can still use it by using the detector probes. Okay. So here's just some examples of different layouts of different scopes. Remember how I said they're all kind of laid out somewhat logically? There's a couple of different examples to kind of show that. This is an old 454 scope. I think I saw one. I think there's one here, standing up there on the table. You can kind of see the vertical controls for channel 1, vertical controls for channel 2, all grouped together. You'll recognize the position controls, the coupling controls, the sensitivity, the input. Here's the horizontal controls for the A and B, A sweep or B sweep. Triggering controls right down here on that scope. Here's the display controls, intensity, focus, that kind of a thing. But generally group those functions together so you can kind of attack them, one at a time. Okay. Here's another example. Here's a channel 1, channel 2. Here's vertical controls for channel 1, vertical controls for channel 2, horizontal controls. It even says vertical, horizontal, and trigger. Okay. So if you look at it, it's a sea of controls, but they're really laid out kind of logically, so you can kind of work your way through it. Okay. So again, set your scope to an automatic, an auto trigger, so you can get a sweep. Okay. You can play with the trigger controls later to stabilize a waveform. Okay. Start off with a relatively high volts per division. Work your way down. Okay.
Read the words.
Read what it says. It tells you right on there what it's doing. Remember, if you got a 10x probe, you multiply these numbers by 10. If the scope doesn't tell you automatically. Here's an example of similar to the scope that we've been looking at on my table here. Volts per division. There's all the vertical section, the horizontal section here, trigger section here. This happens to be a 4-channel input scope. Okay. Here's another example here. This is very similar to some of the other scopes here. Channel 1, channel 2, horizontal trigger. So you'll see they'll either be color-coded, sometimes grouped together. Some of the newer scopes do a better job of laying them out. This one's a little bit like a puzzle. Okay, but they are kind of laid out in about the same area. Okay. So take time to look at your scope, get familiar with what you have and where the controls are so you know where to go set things up. So I got a pop quiz here. Okay, see if you were paying attention. So if I'm looking at this sinusoidal waveform coming out of the wall outlet, which of those measurements can I directly measure very easily on the scope? Which one can I make?
Oh, peak to peak.
Well, the peak to peak I can make. That's easy, right? Which one can't I make?
RMS.
RMS. RMS. Right? The RMS is like some value that you got to calculate from the peak value, right? So you don't measure that directly. So that's good. Okay. Nobody fell asleep. Everybody paid attention. Passed the quiz. Okay. So again, it really gives you a view of what's going on with voltages over time. And I always like that because as a design engineer, I try to always picture things visually. Okay. When I'm looking at a circuit, trying to understand how it's going, I'm visualizing voltages kind of being higher or lower, in elevation. It's what the scope is showing me, right? So you can look and say, okay, this is a high voltage, this is a low voltage, I got a big difference in time to climb across here, I got a lot of voltage across that component, or I don't. So I kind of think the way a scope shows me things. And I find it very, very intuitive, and you can learn a lot. It doesn't replace your Simpson 260, okay? It doesn't replace a lot of the other tools that you have, but you can use them. You still use it for a lot of those things. You can get approximate DC readings, for example, if you want to do that, but you can break out the voltmeter for measuring that. Okay, but if you want to look at what's going on with this, I'm tracing a signal through an amplifier. Okay, and I'm listening to it and it's distorted. Why is it distorted? Maybe I got some hum on it, or it sounds like it's raspy or something like that. You can look at it and say, well, I inject a perfect signal in, and I look at that in the scope, it looks good. I can walk my way through the circuit and see where things get bad. Where does it not look like that anymore? Okay, and why? Okay, those are the kind of things that really help you identify what's going on in a circuit in a certain area. So, I do have a couple of other backup slides here. People who want to talk more about things like a trigger hold-off control or dual delaying time bases that a lot of these scopes have. We can go back and play with that stuff, but I wasn't going to just talk about that until people are really interested, because I think we all want to go play with this stuff. Yeah.
Alan, obviously we're anti-radio club.
Yep.
We work with vacuum tubes.
Yes.
Should we be using vacuum tube oscilloscopes?
Well, how much of a purist are you, right? So,
Are there vacuum tube triggered oscilloscopes?
oscilloscope.
Absolutely there are.
No.
So you don't have to be using them though. There's really nothing different. The performance generally of the solid state scopes is going to be better. You're going to wind up having higher bandwidth scopes and things like that. With the transistorized scopes, you just have to worry about voltage ratings. Okay, how much voltage am I applying to that input, and will it damage the input of the scope? You got to look at your probe and the scope to decide. Now, for example, if the scope says it can only do 300, but you got a 10x probe that says it can do 600. Okay, what do you do? Okay, what is it? Well, if you plug the probe in, okay, the scope will see the 600, but the scope's only going to see 600 or 60, right? It's going to divide it by 10 by the time it gets there. So that's okay. You can do that, right? But don't put that probe in a 1x volt, okay? Because then the scope would see the 600 volts, right? So,
Yeah.
You got a question? Yeah.
Is it harder to damage a tube scope?
It depends. Because the damage that'll happen generally will be, remember we talked about the vertical section, the first thing it sees is the attenuator. The design of that attenuator is what's going to determine whether you can damage it or not with an input. So in general, are the attenuators built into tube scopes more robust or can handle higher voltages than the transistorized stuff? Maybe.
Say a couple words about burning screens.
Okay. So you'll notice I've left these scopes sitting on here for a while.
Yeah.
Most of the modern scopes, anything that's 30 years old or less, are generally pretty good. Some of the older scopes, this is kind of before a lot of the CRT technologies were kind of perfected. So it's certainly possible that if you have an image that doesn't move and is turned up really bright, sitting in the same spot on the screen for a long period of time, you could potentially burn the phosphor on the face of the tube and essentially make that spot dim forever. Okay, something that was very common in some of the early computer monitors, right, that you would see, but the same thing can happen on the scopes. Especially if you put a scope in like XY mode and you have nothing going in, that electron beam is sitting in a dot.
Yeah.
And so it's whereas a sweep, it looks like I've got something there all the time. The reality is it's always moving. So the duty cycle, if you will, of how long it's sitting in one spot is pretty low. But if you go to XY mode, the thing's sitting in a dot in one spot, that electron beam is firing away at the phosphor. It will most likely burn the phosphor at that spot. And eventually that spot will go dim. Okay, never to be lit up again. Okay.
So could you turn the intensity down?
You can, absolutely.
Just turn it all the way
Turn the
down?
intensity down.
Instead of switching to some other...
Yep, absolutely. Yep. So if you have a 100 megahertz scope, that means it's rated to be, the response will be down by 3 dB at 100 megahertz. Doesn't mean that at 101 megahertz you don't see anything. It just means its response is down. Okay. So the higher bandwidth scope will have a flatter frequency response over a lower frequency range for looking at signals. Okay. But again, it's not necessarily unusable above that frequency. So now, how much bandwidth do you need? The question is, what do you want to do? 30 megahertz or above is probably ideal for what you guys are working on. Okay, because most of the radios are shortwave radios. Something in the hundreds of kilohertz to 30 megahertz, typically what you're looking at. Maybe a local oscillator might be just a little bit above that. Okay, so if you want to actually look at the local oscillator swing, okay, you might want to have enough bandwidth to literally see that. But it's not absolutely necessary. Right? If you have a 10 megahertz scope, it could be perfectly usable. Some of the IS might be at that frequency or less, or even if it's a little bit higher, just the amplitude won't be full. Maybe you can't rely on it to give you the full peak-to-peak voltage that you're seeing, but you can still look at the wave shape. Okay, so I wouldn't be too hung up on it. But if you can get a 50 megahertz scope for the same price as a 100 megahertz scope, get the 100 megahertz scope. Okay, but for what you guys are doing, probably anything above 40 or 30 or 40 megahertz probably don't need. But it's nice to have. Because the problem is that at 100 megahertz, the response isn't exactly as it is at 10 megahertz, right? It's a 100 megahertz scope. You're down 3 dB. Okay. So if you have a 200 megahertz scope, you'll probably be pretty darn flat at 100 megahertz. Okay. I mean, this 465, you see a lot around. They're 100 megahertz scopes, great scopes. This one next to it is a 2445. That's a 150 megahertz scope. There are versions of that up to the 2465 that were up to 400 megahertz of bandwidth. Which might, one of the higher ends that you'll see in the typical analog scope. Okay. But a lot of these around, I've seen everything from 20 megahertz scopes, 10 megahertz scopes, 30 megahertz scopes around. Any one of them would be really good, do you really well. Especially if you're tracing through like a 455 IF or some audio circuits and things like that. That's more than enough. Okay. Yeah.
Now,
most oscilloscopes now, like the LCD digital,
Yeah.
do you get a nice clean sine wave, or is it a little choppy?
Well, it's a good question. Most of the digitizing scopes use a 8-bit D to A converter, okay, which means that any voltage coming in is sampled and is, so the voltage that you see vertically is one of 256 values, okay? Now 256 values spread over 3 or 4 inches, you really can't see the stair step, okay? And the traces will generally connect the dots, if you will. So you generally don't see the effects of the digitizing. The thing that you can get into with digitizing scopes is something called aliasing. Okay, that's a whole other issue where if you're looking at a signal, say at 10 megahertz, and you dial the sweep speed way down, the sample rate will go down to the point where you get less than 1 sample per cycle. So that when the scope assembles the dots, it looks like some other frequency, not the 10 megahertz signal.
This is why the wagon wheels turn backwards in the old cowboy movies.
Exactly. Exactly the same concept.
And the Batmobile too.
Yep. So but yeah, that's exactly the same concept. It really is a topical aliasing, and it can happen a lot more in digital scopes, and it will not happen on analog scopes.
Does Tektronix, I'm just curious, do they still make CRT scopes or no more?
Tektronix does not make them anymore. There are some companies that do, and they're generally lower cost scopes too. That you can find out there from people like Leader and Hitachi and some of the other companies like that. There are people that make them still new as analog CRT-based scopes, but they're priced more than they're higher priced than what you probably want to pay. Okay, but a lot of the scopes that you see here, you can find online or at Hamfest or flea markets and things like that. For $100 or less sometimes. Yeah.
What was the transition scope in Tektronix, vacuum tube to transistor?
It's a good question. There were a couple of scopes in the late 60s. The 454, I think, was one.
422.
Yeah, the 422 and the 450. I think it was the 454 that was the first one that the early versions of them actually used nuvistors.
453s. At a certain serial number range.
Yes, they switched from nuvistors, from vacuum to the nuvistors, and nuvistors to BJTs or something at that point. That was about when that happened. So anything from the 70s on up was generally solid state, except for the CRT.
And the 453s have a super sharp trace.
They're really
it's like razor sharp.
It's really nice. Yeah, they're really nice scopes. So some of the 400 series scopes actually have better trace clarity and crispness than some of the newer ones. So
Actually, the thing with the 500 series that burned in is they had a really delicate fine trace on them, and you were going, there's nothing to protect you.
It was very intense in one spot. Right?
Yeah, so, the solid state scopes really have sort of a fuzzier, nastier image on them, but they don't burn and they'll take off in this treatment. Right. You don't have to try and find a jug for them someplace. I used to do surplus, and that used to be these huge issues. Where the hell do you find the scope to?
Right.
The Tektronix was selling them for good money.
Yep, absolutely. All right, any other questions?
There'll be lots as you go around.
Yeah, I think Alan gets
I've brought a few samples here, essentially the history of oscilloscope tubes. And an adjunct to Mr. Tektronix here, I can show the development of the CRT through the ages, and including a couple of, I guess you call them high points at which caused the development of a whole new class of oscilloscopes as time went on. And with the help of the museum over there, we have a scope tube here in the nude, and you can indeed see the electron gun, the cathode at the top, a couple of accelerator electrodes, and you can see the deflection plates. Here's the, I believe it's probably horizontal first, and then vertical first, and then horizontal. And then you can see the phosphor screen. And then from the back of it, the side that the electron beam strikes, you can get to see that too, because this one lacks its internal shielding, the aqueduct coating, so you can come up and see that. But this represents the first style of CRT, developed around 1930 some odd, and it allowed some of those early World War II radar units to be built. For instance, this is a World War II radar oscilloscope display tube. The feature there you can see it's got a high voltage accelerator on it, and it has the aqueduct coating, which is part of the acceleration. And then it has a simple screen. This style screen has a long persistence. Remember the mention of persistence for the eye. Since the radar beam is something that travels around in a circle in several seconds, you need to store an image. This is an early way of doing it. It's a phosphor that lasts for about 10 seconds once lit. So this is roughly 1940, 1942 kind of thing. Then they were able to make it bigger. This is the kind of tube that you would find in the synchronized sweep, non-triggered synchronous sweep oscilloscope made from 1938 or so up into the early 50s. You can see the same structure here. You can see the electron beam. And the style of oscilloscope that you could build with this kind of a tube is a kind of a low-frequency affair, because it took a couple of hundred volts to deflect that beam from side to side, because the entire acceleration velocity of the beam was present the same from one end of the tube to the other, because the acceleration was applied right about here within the tube. And the electrons passed through the deflection plates very quickly. So it took a lot of voltage to move them. And that's one of the key points in the design of the CRT. A little later on, your friends down the road there at Hewlett-Packard developed a flat screen for a CRT. This now allowed you to put a graticule on the front of that tube and actually read a voltage without having to read around a curve with your eyes. So this was a great development. But still, this is only a couple of hundred kilohertz to a few megahertz. But it made a passable oscilloscope, and a lot of these you'll find at flea markets in the 120 series, Hewlett-Packard scopes, often in a rack mount. And they make good scopes for doing sweep setups and things like that. But the real breakthrough that I think we can attribute to the Tektronix folks is what's called the post-deflection accelerator. You see this tube has a spiral down it. The principle that this thing works on is that the beam passes through the deflection plates at a very low velocity. And the amount of deflection you can get is a product of the time that the electron spends within the deflection plate and the amount of voltage that you put on it. So if you can go with a slow beam through the deflection plate, now you can deflect that electron with just a few volts. And anyone who's tried to build a wideband amplifier knows that getting wide voltage swing at a very high frequency is a very difficult thing to do. So the fact that they could get this beam to deflect side to side with only maybe 20 volts was the thing that allowed them to build 25, 30, 50 megahertz oscilloscopes in the vacuum tube era. This was the serious breakthrough. The way the spiral works is the screen is at 10 kilovolts on this button. The deflection plates are about ground, and the cathode is around minus 15 or 1.5 kilovolts. So all of the deflection, all of the acceleration of the beam happens in this space, and it happens in a tapered manner from the spiral. I don't know whose patent this is, but it was worth billions and millions of dollars. Great one. Then from there on, it's only been shrinking in size. This is a CRT from a television style monitor. It's the flat face, and indeed this one you can see a little burn line on there. That's what you often get from a fixed display, something that displays the same kind of signal over and over again. This allowed space saving, because now you've got something that is ground with a square trace on it. It actually kind of shapes about the waveform you're trying to watch. And then we come to the scope tube that's used in that 453 back there. And once again, its breakthrough is what they call an internal graticule. Any of these other CRTs required a faceplate with some lines etched on it so you could read the voltages. This one is inside the tube. And the wonderful thing about that is that you can look at it from any angle and not have a parallax issue, because you're writing on the same surface on which the graticule is also placed. That was another nice breakthrough. And the last breakthrough is actually back in this tube. This breakthrough allowed them to get from 30 megahertz up towards 100 megahertz. And if you look real closely inside this one, you'll see there's a bunch of coils in there. What they've done is they've actually cut the deflection plate up into sections and then provided a coil, a little matching network from one plate to the next, to the next, to the next, to the next. The purpose of this is to match the velocity of propagation down this structure to be the same as the beam of electrons that's passing through it. And the result is they get the best and flattest deflection sensitivity all the way out to 100 megahertz. This technology is still in use, even in the most modern ones, the CRT. So that's kind of how it went until LCDs knocked everything out of the market.